input. It is on my input 1 or 2.
Okay, this is the volume themes.
Actually, something is. Wait. I know what it is. I don't remember what. Let me check this one again. So I get the exact phrasing.
Maybe from property.
No.
Discord audio, not
Input V, okay. Discord audio, okay. Sound good, Discord.
Okay, here.
Yeah. Go on to settings.
Oh, yeah.
Audio. The video audio. Yeah.
Yeah, input true and.
Mixerless.
Meanwhile, we have here. Okay, this one is working.
Yeah. No, the problem is with the passing of the computer, obviously, but that's okay. Did you check the sheets for you?
Yes. Yeah, and it's going to start right now.
Yeah. So we're gonna leave it to it. Sorry for the slight interruption.
It's okay. All right, so it's time, right?
Yes.
Is it live now, the video? Okay, all right. Thanks for coming to the opening of the Unsound workshop. So I'm Lionel Parot, one of the 3 co-organizers of the workshop. Unfortunately, the others 2 cannot come today, so they will participate remotely. Okay, so this workshop is about the sources of unsoundness in type systems and verification. This is the 2nd edition of the workshop, which had the 1st edition in SPLASH' 2022. We're maybe thinking of having it every 2 years. So here's the program. We have actually 2 talks in the morning, in addition to this one. And then a few more in the afternoon with 3 remote talks, actually. One of the presenters was supposed to come, but he was stranded in the airport, and he's going to give his talk in the airport. So what are the goals of the Unsound workshop? So our goal is to discuss all aspects of unsoundness in type systems and verification systems, and to have a discussion about what these sources are and how they can be addressed. And we also want to discuss previously known or new sources of unsoundness and how they affect the day-to-day of researchers, but also actual programming language users. So in this welcome, I will just quickly introduce the subject matter, give some historical background, and a preview of today's talks. Okay, so first of all, what is unsoundness? It's good to be clear about what we mean here. What I think is a good way of describing it is that it's a mismatch between what the type system of a tool or what guarantees a tool is supposed to give you and what actually happens in a real system at runtime, for example, right? And so a sound tool will validate a subset of the correct behaviors. It may not be complete, so it may not be able to validate all of the correct behaviors. And an unsound tool will actually include some incorrect behaviors and while telling you it's correct, right? And so one of the most well-known historical examples of unsoundness is in languages like Java or C# or many others where arrays are covariant. And so this is a problem, right? It is a source of unsoundness, as I just described it, because it makes the type system claim things that are just not true. So basically, the covariance of array means that if you have a type string that's a subtype of object, for example, then it says an array of string is a subtype of an array of objects. And this is a problem because if you consider this example, if you create an array of strings and then you upcast it to an array of objects while still retaining the original reference, XS, it allows you to insert elements inside this array that are not actually strings, because the upcasted type says this is an array of objects, so you can insert objects into it, and 42 is an integer, which is an object. But then the original array still points to the same thing. The original variable still points to the same array. And so the same array is going to now receive values that are not actually strings. Okay? So it's a problem with interactions between mutability and subtyping. Another famous historical example is that of covariant method parameters. So at some point in the 90s, people argued that you could refine the types of classes, of class methods, so that, for example, if you had a base class that had a function foo taking an object and returning an object, you should be able to make a subclass where foo is refined to take a string and return a string, right? And it kind of makes sense with this natural idea of refinement. And many programming languages actually originally had that, including the FL programming language. But it's also unsound. For example, take this very simple example where we refine the type of a function, including the type of its parameter, so that it then accesses the length of its parameter, which is assumed to be a string now. But again, if you upcast an instance of this class, losing information about that refinement, then suddenly you can call the method with objects, including integers, and you have a problem again, okay? So this one doesn't even use mutation, but it's a very similar kind of problem. So there are better solutions to this kind of problems, right? So instead of using covariant mutable arrays, you can distinguish between mutable and immutable arrays, separating their different interfaces, and then you can have the subtyping relationships you want, so that, for example, a mutable array is actually a subtype of an immutable, a mutable array of string is actually a subtype of an immutable array of object, right? So a read-only array of object. That's fine. It's sound. And for covariant parameter type refinement, actually what you probably want is something like type classes, or alternatively f-bounded type parameters or multiple dispatch. Well, there are many ways that you could solve this problem without having unsoundness. A fun fact about TypeScript is that it has both sources of unsoundness. Okay, so it has both covariant arrays and covariant parameter. In fact, it has bivariant parameter refinement. And that's because really TypeScript is more of a linter, right? It's not really providing you any strong guarantees or any guarantees at all. And you can summarize the design philosophy of TypeScript type system as YOLO, right? You only live once. So there's an interesting talk by the creator of TypeScript where he describes how recursive types are checked for subtyping, and basically the TypeScript type checkers, TypeScript type checker expands the recursive types a given number of times, and then it gives up. But when it gives up, it doesn't throw an error. It just accepts that the subtyping probably holds, and that's of course unsound, right? And again, there's a better way of doing things. If you do care about the guarantees, so for example, you could restrict the recursive types to be regular, or alternatively parametric, which makes subtyping decidable, so you don't have to stop and just give up. All right? On the other side of the spectrum, soundness may be very important, right? So in verification, if your system is unsound, because of the principle of explosion, basically you can make it prove anything you like. So that defeats the purpose of verification, most probably. And in the last Unsound workshop, actually, we raised an issue with object-oriented programming and some verifiers that support object orientation, and that were found to be unsound, because actually object orientation does interact in possibly surprising ways with soundness, with verification, right? So we actually have a talk this afternoon about this problem and how we can solve it by using a better principled approach to deriving an object-oriented system from a functional programming one. So when does unsoundness arise? As you can tell, it arises when different features interact. So features in isolation may look fine, but when you put them together, suddenly problems occur, right? And it's often unsuspected. Often you see different things that seem completely fine on their own, but when you put them together, bad things happen. For example, side effects, right? Mutation and exceptions, they make many things unsound, actually, that would be sound otherwise. So typical example here is a polymorphic generalization in ML, right? If you generalize the types of values without a value restriction, then you get problems. But also you have problems in metaprogramming and path-dependent types and things like that. I highly recommend this website by Stephen Dolan with help from a few other people, which has a very good list of examples of unsoundness in type systems. It's very fun. You can see that many of the examples I talked about are, actually all the examples I talk about here are in this website, and they're well documented and well explained. A favorite of mine in this list is when two obviously orthogonal features interact, which are general algebraic data types, which support a kind of reasoning that we refer to as GADT style reasoning on one hand, and multi-stage programming on the other hand, which are completely different things, right? So one is a type system technique that tries to discover more type information at runtime based on what you pattern match by refining the types of the scrutinies. And on the other side, you have multi-stage programming, which is just a technique of generating code while making sure that the output is well typed. And so here's probably the most concise way of expressing the problem is in Scala. It's not exactly using a GIDT, because in Scala GIDTs take a bit of a different shape, but it basically explains the source of the essence of the problem. So here we have an abstract class that has a type member, right? So this type is attached to all individual instances of the class, and each different instance may have a different type definition for A, okay? And we are giving it two bounds, one lower bound and one upper bound, and these two bounds are not consistent, right? So this lower bound says A should be greater than any, but it should also be a subtype of nothing. So n is like the top type, and nothing is like the bottom type. And this is obviously not true unless your type system has only one type, right? So basically you cannot create objects. You cannot create instances of this class, right? It's like an uninstantiatable class. And in type systems, like Scala's type system, you cannot really statically prevent such bad bounds from being expressed. It was tried for a long time, and it's not really possible to statically prevent all bad bounds. And so as long as you have bad bounds, you have a problem with metaprogramming, which is exemplified here. So here we have a little tick before the curly braces, meaning it's a quote, so it's building a new program representation at runtime. And that program is a lambda abstraction taking parameters x of type t and returning a body which is evaluated as follows. So the $sign basically escapes the quotes and evaluates something at code generation time. And here we are just providing the value 42 and saying, oh, by the way, this has type x.a. Okay, and so what is x.a? Well, it's a type we don't know because we don't know anything about x. We just know it's a t, right? But we know it's greater than any, so surely 42 is less than a, right? We also know that it's less than nothing, so it's good enough as the type of the result here. And that's a problem because it means you're going to generate code that's actually ill-typed. And you could even crash the program generator itself without even running the generated code. Because the source of the problem is that it's fine to have bad bounds in Scala, provided that you can only use them when you have an evidence that the type is inhabited. So when you have a variable of that type in scope. But here, the variable is not actually there, right? It's only there in the future stage. So this code will never actually, this function that we're building will never actually be called. But because we escape the body, we escape the quote, and we execute code directly, we're making use of a value that doesn't exist, X. And so it's not an actual proof of the property that any is less than nothing. Does this make sense, or do you want me to explain it a bit better? Yeah. And so what I found particularly interesting about this this bug is that it arose in OCaml first. Someone found it in OCaml, and we could directly port it to Scala, which is a completely different language. So I opened an issue in the Scala repository, and it's still open to this day. What's really interesting is that OCaml and Scala basically share nothing in terms of foundations. They have very different foundations, right? So OCaml has is basically a simply typed linear calculus plus some other bells and whistles, right? Like row polymorphism, recursive types, and GADTs. And in particular, it doesn't have implicit subtyping, and it has problems with types like top. So it doesn't even have a top type, which would cause problems. But Scala 3, on the other hand, is like fully subtyped. It has a top type. It's based on a completely different foundation where functions and type parameters are not even first class. They're like syntax sugar. And so it's funny that even though the foundations are completely different, you have essentially the same bug that arises in these two contexts, right? Okay. So let's look back at this this historical example of a bad subtyping relationship, array of string less than array of object. Actually, we can make it sound by making sure that the array is linear, right? So this actually works. It is fine to say that this subtyping holds as long as array is linear. So why is that? How can you understand this? And this is one of the things I will talk about this afternoon in my contribution to the workshop. It's related to eta expansion and how to understand subtyping. Okay, and I would like to conclude with a quick note because we are already out of time. I think that the notion of safety is relative, okay? Soundness itself is a bit relative. And for example, you can consider that, well, obviously we all know C++ is very unsafe, right? And it can lead to vulnerabilities and memory corruption. And so if you sandbox things by putting everything in WASM, for example, it's obviously safer, right? The program may corrupt its own memory, but it's not going to cause problems like vulnerabilities in the outer program. But it may still corrupt its own memory. On the other hand, if you build your programming language on the Java virtual machine, as long as you don't make use of unsafe APIs, which most Java programs don't really do it, or at least not directly, and certainly most Scala programs don't do it, then you have even more safety because the program may no longer corrupt its own memory, right? So it's like a very safe little sandboxed runtime where unsoundness doesn't matter as much, right? Because if your type system is unsound, it's not going to lead to memory corruption and possible vulnerabilities. Rust, on the other hand, is often touted as a very safe language, right? Because it guarantees lots of things at compilation time, such as memory safety. Or does it? Well, not exactly, because it has many holes, right, in its type system. And a hole in the type system of Rust is much more serious, because it doesn't have this sandbox and this background guarantee about the programs and their memory. And so when this paper came out, Scala and Java's type systems are unsound, it generated a lot of talk, and it was kind of sold as like a very bad result, like, oh, we found out Java and Scala's type systems are unsound, they're worthless, right? And a lot of people have used this to criticize Scala, for example, to discount it, right? But actually, there were already many existing cases of unsoundness, like coherent arrays, and null itself is kind of unsound, right? Null is a value that says it has an e-type, but actually it doesn't really. If you use it, you have an exception. This is basically unsound, right? And so this paper isn't really that new, and it doesn't say as much as it appears to, right? And yet another sound, another source of unsoundness that we found recently will be presented in this workshop. It's about inner classes in Java. So you can attend it to know more. And I will just conclude on this note that most practical programming languages have plenty of sources of unsoundness, right? Some are well known and avoided by programmers, and some are not actually known, and they may cause problems. And so that's how I will conclude this introduction. And so let's talk about these problems. Okay? Thanks. All right. Any questions? So we don't have much time. No Discord questions, right?
No Discord questions.
All right. Okay. Yeah. So.
Back at 11.
Okay.
think I'm gonna run out of battery, but just in case. It doesn't.
So, are you Gaspar?
Yes.
No, the blackboard is full.
Okay. Don't worry. No problem.
Okay, I think. Just make sure you didn't turn on the night shift mode, because it changes the color tone of the screen.
No, I
Yeah.
don't think so.
Yeah, let's check here.
Here?
Yeah, click.
Mm-hmm.
How about here? I think there's like a menu. Okay, so it's off.
Yeah.
Make sure it's off. Yep.
Okay.
The HDMI cable.
So, you said Richie?
Richie.
Yes, Richie. Alright, so should we start now?
Let me introduce you, okay?
Yes.
Okay, so now we have our first talk about taming unsoundness with gradual abstract interpretation by Gaspar Ricci. Please.
Thank you. Hello, everyone. Let me start the presentation here. Okay. Well, hello, everyone. My name is Gaspar. I'm a student at the University of Chile. I'm currently pursuing my master's degree. And today I'm going to talk to you about gradual abstract interpretation and how we could use it to tame unsoundness in program analyses. Right? So gradual abstract interpretation is a project that started very recently, and it is a group effort. We have a team, Chilean team based in the University of Chile, integrated by me, Matías Toro, Eric Tanter, David Ibáñez, and also a German team at the University of Mainz, led by Professor Sebastian Erdweg and his PhD student Armand Legault. And yes, well, now we can start. So our starting point is the world of static program analyses. So just as a quick refresher, an analysis is a procedure that takes a program, makes a prediction about that program's behavior, and gives us a result that is a conclusion that is derived from that prediction, right? So for instance, we could have a null pointer analysis that predicts which pointers are null at each step of the execution of a program, and the result could be warning us when we could be dereferencing null pointers, right? So one way of doing program analysis is with abstract interpretation, right? This is a very famous mathematical framework that was proposed by Patrick and Radia Cousteau in the late 70s. And to illustrate it, I'm going to use this program as an example. This is written in a language that only has integers as values, right? So we have a factorial function that computes the factorial of an integer, and it receives input from the user and calculates the factorial of the number it receives, right? So one thing we could do is concrete interpretation of this program, which essentially means that we are actually going to execute it, right? So in this case, we would be working with the concrete values, the integers, and we would have concrete operations, right? So for instance, the user could give us the number 4, and after computing the factorial, we would get the result 24. Yeah? Nothing mysterious here, we're all very used to this. Now, on the other hand, we could do abstract interpretation of this program. So instead of working with the concrete integers, we would work with an abstraction of the values, right? So for instance, we could use the sign of the values associated to the variables of this program, right? And we would also have abstract operations, so operations that work on the abstract values, right? So in the framework of abstract interpretation, the abstract values form what's known as a lattice, right? So in this case, we have the abstract value minus, which represents the negative integers. We have 0, which represents 0, of course, and plus, which represents the positive integers. And we also have 2 special values. So the most important one for this talk is top, which represents all integers, regardless of their sign, right? Now, this lattice is equipped with a precision relation and also with a very important operator called the join, which gives us the least upper bound between two elements of the lattice, right? So for example, the join between 0 and plus would give us stop, right? Now let's see how abstract interpretation would proceed on this program considering this abstraction of the values. So firstly, the user is going to give us an integer as an input. But since we're not actually executing this program, we don't know which integer we are going to receive from the user. So the only thing we know is that x is associated to any integer, to the top element of the lattice, right? So we can call this factorial function on that argument. In this case, n is associated to that top element, right? And we can proceed with the execution. So here on the first line, we would learn that the variable res is associated to a positive integer. And then when we proceed to the while, we have a question, right? Do we go in the while? Do we go around it? We don't know, because n can be any integer, so we don't know if this guard condition holds or not, right? So what we're going to do is follow both paths and then join the results we get from each execution flow, right? So if we go around the while, then we know that n can be any integer and res can be a positive integer, right? Which is what we derived before we entered the while loop. And if we go in, we can learn a bit more. We can do something that is called path-sensitive analysis. So from this guard condition, we can derive a bit more knowledge about n. So for instance, n, we know that is greater than a positive value, so surely n must be positive as well, right? So at the entry of this while, we know that both n and res are positive integers, which means that when we go to execute the next line here, we know that we are multiplying positive numbers, so we know that the result is going to be positive, right? And in the case of n, when well, we are subtracting positive values. So since we don't know the absolute values of n, we can know for sure the sign of the result, right? So that's why we get top as an element, right? So now it comes the time to say, well, what is the final result of res? So to kind of compute this, we are going to join the results we got from the branches of execution, right? So what's important to notice here is that res is associated to a positive integer in both branches, right? So joining positive and positive lets us conclude that res will be associated to a positive integer when we reach this point, which means that the factorial is going to return a positive integer no matter which integer receives as argument, right? Now, for transparency, this abstract interpretation runs in a fixed point algorithm, so it needs to, in order to find a stable solution. So but you can just believe me that this is the solution it would reach, right? Now, we could use the result of this analysis, right? So for instance, if we had this program, which receives input from the user and calculates the factorial of that number, and then based on whether that result is positive or not, it takes one or the other branch of this if statement. We could use the result of the analysis, which means that since we know that it returns a positive integer, we know that this condition is always going to be true in every execution, right? So this would mean that this branch is never executed. It's dead code, right? So we could proceed and eliminate this and only leave the body of the true branch of the if statement. This is great, but there is a problem. It can be, the analysis we used can be unsound. Okay, we assumed that multiplying two positive integers always yields a positive result. But in a language with bounded integers, this could be false, right? If an overflow occurs during the multiplication, the result could be negative or even 0, right? Which means that in some executions of this program, this condition could be false, and we would actually need this branch of the if right? So it cannot be deleted. Okay, it cannot be considered dead code. A sound analysis would be forced to assume that the multiplication of positive numbers is top, right? It could give any integer. But this is very imprecise, right? And generally, when we are in the world of program analyses, and particularly static program analyses, imprecision is one of the greatest enemies, right? For instance, it could prevent optimizations that are perfectly safe to carry out. This example is not the case, right? But it could be. And another problem that could cause, that imprecision could cause, is that if we are using an analysis to warn users about potential bugs, then imprecise results could make the analysis warn the user about bugs that will never happen. And this is very annoying and very useless for the user, right? And what ends up happening is that in practice, many analyses sacrifice soundness in order to gain precision. And it is so much so the case that it led some researchers to coin the term soundiness, right? They recognize that many program analyses make use of unsound assumptions, right, in order to gain precision. They recognize sort of a practical need for it, right? Now, what they say is that, well, it is fine if your program analysis is unsound for the sake of precision, but you must be transparent about it. So to prevent situations like the one I explained with the example, when you design a soundy analysis, you need to let the users know which unsound choices did you take, so that the user knows in which scenarios they can act on the results of the analysis, right? So we have seen that optimism is really appealing, right? Because it can help us gain precision with our analyses, but we have also seen that it can break soundness, right? So what do? Do we give up? What happens when we really need the analysis to be sound and precise? So we have a very supportive friend, which is called Gradual typing, and it says, well, don't give up. You can check the optimism at runtime. So what we envision is something called gradual abstract interpretation, right? So instead of having the usual analysis, which takes a program and gives us a result, a gradual analysis would also give us an elaborated program. Now, this elaborated program would contain runtime checks that validate that any optimistic assumptions that were made by the analysis is respected in runtime, right? And then the results of the analysis will be sound with respect to this elaborated program. Yeah? So in a sense, this is inspired by the notion of soundness or gradual soundness, which is soundness up to runtime checks and runtime failures, right? Oops, I pressed the wrong button, sorry. Okay. So if we go back to our factorial function, a gradual analysis would reach this line, and it would consider two possible results. So on one hand, we would have the sound assumption that the multiplication of two positives yields any integer, right? So the analysis would compute that res is associated to any integer, and also it would compute the optimistic result from this assumption, this optimistic assumption, right? From which it can derive that res is associated to a positive integer. Now what it would do is compare these two results. So in this case, the optimistic result is more precise than the sound one. So there is a chance that at runtime we could get a result that is not contained in this prediction, right? So in this case, the analysis determines, okay, we need to insert a check here to validate that the concrete values will be in this prediction, right? So it inserts it automatically during the analysis. So in this case, the runtime check would be to basically validate that the result of this multiplication is positive, right? So now if we take back, so basically the analysis would now give us this elaborated program, which is the same one we saw before, but now the factorial function has this runtime check. So the gradual analysis would conclude that this factorial function gives us a positive integer, right? But now we have a runtime check that validates this assumption at runtime, right? So now we can say, okay, this condition is always true. It can be false, but at least we know that if it is, then this will trigger an exception. And this let us say, okay, this will never be executed, so we can now safely delete it, right? So what we have been currently working on, or what we have been working on in the past couple of months is, well, in the implementation, we have been exploring a gradual sign analysis like the one we saw in the example. Very recently, we also completed a gradual interval analysis. Here, the abstraction, instead of being the sign of the values associated to the variables, the abstraction is an interval, right? And we have also implemented the, well, at least a proof of concept of how the runtime checks would be inserted during the analysis. And to do this, we have actually been using a very cool platform called Sturdy. Sturdy is a platform that allows you to build a static analysis based on big step abstract interpretation in a modular way. So Sturdy provides a library of reusable components that you can bring together to build your analysis. And the cool thing is that you can prove the soundness of each component independently. So by construction, you have a sound analysis if you use this components. There's a lot of theoretical background on this cool platform, right? And on the theory side of things, we have been exploring what this gradual soundness notion would be, and also if we could somehow adapt the gradual guarantees that that basically were put forth when the refined criteria for gradual typing was published. Okay. And yeah, well, as I said, this project is just starting, so there are still a lot of things to do. So we have many questions. One of them is, what is the impact in the performance of the elaborated program when we consider the runtime checks that we are inserting? We need to explore which other optimistic assumptions are being made by real-world analyses. We need to continue to explore the meta theory of this approach. And above all, we need more real-world applications of this approach. So it would be very, very interesting to discuss this further if you have any ideas, right? And one idea that we have been wanting to explore as well is designing an annotation system that would allow us to have local control of the application of the optimistic assumptions. So for example, with these annotations, we could tell the analysis, okay, assume these, but only in this portion of the program, nowhere else, right? And this would be very useful when the user wants to make use, or well, more like legitimate use of certain aspects or characteristics of the language. For example, some hacky use of overflows or bit magic or something like that, right? So to sum up, what we propose is gradual abstract interpretation. Basically, we say that, okay, it is okay to use optimistic assumptions to increase the precision of our analyses. And, but the key thing is that we want to make sure that these optimistic assumptions are being respected, so we are going to check them at runtime to preserve soundness. And one cool thing that we want to achieve is that these runtime checks should be inserted automatically during analysis using the logic I presented. So in the end, we would get this kind of diagram of a gradual analysis that gives us results, but also an elaborated program with runtime checks, with the results being sound with respect to this elaborated program. So, well, that's all I had prepared for today. Thank you very much for your attention, and I'm open for any questions or comments you may have. Thank you.
All right, any questions? I can start with a question.
Yes?
Hello? Does it work? Okay. Yeah. All right. Thanks for the talk. So I was trying to understand the use case that you presented about sign analysis.
Mm-hmm.
So your goal is to make use of unsound analysis for optimization, or for optimizing other things in runtime, maybe the code size or something, so that you can drop this dead code. Is that the goal?
Right. I mean, we have thought about two main applications. So one would be to allow optimizations, but the most important thing is that we want to prevent optimizations from changing the behavior of the original program in ways that would be nonsensical, that
Mm-hmm.
would be unexpected for the user. So we want to prevent giving results that, when acted on, would introduce silent bugs into programs, right? So
Right. Yeah. Mm-hmm. So you conceptualize your work as like some extra sanity on top of existing optimization approaches, right? Like maybe you want to work on current optimizers and add some graduality to their analysis. Is that how you should think about it?
That is one of the things we would like to do.
Oh, so what was the other thing?
So I actually have another example I can show you. It is very silly. I mean, the example I presented is very, very silly, but so here we have, for instance, a program that gets a list of ages from a database, and it calculates the average of those ages, and it makes a decision based on that average, right? So here we can also have the problem of overflows if this list is very large, right? So in the case that this average results to be negative, here this condition would be true. And even when the real average would be above 0 and above 18, we would be taking this branch and basically introducing a silent error in the program, right? So in this case, we would be using the analysis not to justify an optimization, but to basically insert checks that would validate assumptions here that could lead to potential errors in the final program, right? So the elaborated.
So it's like a sanitization pass.
Yeah.
If you think of memory sanitizers, for example, to check C programs that they don't do bad memory operations, for example.
Okay, yes.
And here you would check something similar, but for overflows.
Mm-hmm.
Okay, cool. So the reason I'm thinking about the relationship with C is because there's the notion of undefined behavior in C, in languages like C, which compilers make use of to optimize programs. And it's an example of a soundy behavior from the compiler, right?
Right, yes.
It's not, if you think of C, if you thought of C as a language with defined semantics, but some things that you allow to be changed by optimizations, then that's what the C compiler would be doing, right? Changing some behaviors,
right,
to optimize programs. And so, could you apply your framework or your approach to the problem of undefined behaviors, maybe by yeah, making optimizing C and C++ compilers more tractable and less confusing when there's an actual undefined behavior.
It would be really, really interesting and something that we really want to explore because it is really annoying when that happens. I mean, there are many, as you say, undefined behaviors that different compilers treat differently and do different things. So yeah, it can produce really unexpected results for the user. So yes, it is something that we would.
Right, maybe it's something you could apply your approach eventually.
Yes.
Okay, cool. So any other questions? All right, let me ask a second question. So I think from what I saw, but I'm not really in this field, many static analysis aren't sound because they want to find bugs and report them to users.
Yes.
So for example, I've seen some analysis do really crazy things. Like for example, they assume that all the loops in a program are executed once, right? Iterate only once. They make these kind of crazy assumptions, right?
Yeah.
This is not something you want to elaborate into some checks at runtime, right? It wouldn't make much sense.
Yeah. So yeah, for these cases, what we could think of is, well, we could have a workflow in which we would use gradual analyses in a checked mode during development to try to use those assertions to catch bugs, and then run them in an unchecked mode in production, right? So that would be a
right, but this wouldn't be a bug, right?
balance.
It's well known that the loops don't execute just once,
Yeah,
right?
Right.
It's not really a way of detecting a bug. So in this case, the static analysis is trying to gain precision by making unsound assumptions, but there's nothing wrong with the source program. And
Right.
if this assumption is not respected, it doesn't mean it should crash, right?
Oh, right. Yes.
So I think this is actually most of this is the case of most of the unsound analysis, which use unsoundness just to arbitrarily reduce the space of programs, right?
That's essentially the subtyping manifesto, right?
Yes.
They're saying, oh yeah, I mean, if we were not unsound, it would be so imprecise, it's also not useful, so let's just not try to be sound.
Yeah. Right. And
It's
that
very unsafe.
yeah, that makes this unsafe to use for obtaining guarantees or for optimization or things like that. And I guess your approach is to bridge this gap and make the same approach usable for optimizations, right?
Right.
But then again,
more than optimizations context, when we would be using the analysis as a lightweight verification tool, like when we need to act on the results.
okay,
And we need those results to actually be good approximations
Right.
of
I
the
see.
concrete person.
So it's also for lightweight verification.
Yeah.
Interesting. All right. Thanks.
Thank you very much.
Thanks the speaker again. All right. So who's the next speaker? Hey, you're Taylor. Yep. Okay, cool. So, alright, can you check your computer? Make sure it works.
Can you turn off the True Tone?
Turn off True Tone.
Yeah. It's a Mac
Yes.
feature of Mac.
Yes.
Do it.
I forgot to remind you.
Yes.
Yeah.
Okay.
So you see the screen?
No.
No?
It's not.
First I have to do this.
Okay.
So it might work now. You see it?
Oh yes.
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 And the live stream is up?
Yeah. The live stream is on.
All right. Okay, so let me introduce the next speaker, Taylor Trush on publishable network contracts in script. And so please go ahead.
Hello all, thank you for coming. I slightly altered the title because I generalized things a bit. I got some very good feedback from the committee, and hopefully this will be a little bit more useful for you guys. There we go. So this is just a brief overview of the type of things I'm going to be talking about. This is a brief outline. And I just wanted to start with the outline because I am part scientist, part programmer, and part entertainer, and didn't want you guys to be worried that I'm going to get to the meat. So this is the meat that's coming. I'm a web developer by trade, not smart like you academic folks. People pay you to push the boundaries of knowledge, educate future generations. People pay me to write websites that sometimes work. 1 million monkeys on 1 million typewriters may eventually write Shakespeare, but we monkeys have already given you the internet with our million typewriters. You guys are wizards, and you've given us web developers many good things. Oh, look at that. You've somehow, beyond all odds, taken JavaScript to TypeScript. That is lovely. One of the wizards over at Harvard, made Elm, which I get to work with on my day job. It's a statically typed beauty. It's a diamond of a programming language. You guys have made Rust lovely, more safety in the world, very, very good. And so I'm here to submit a formal complaint that distributed systems need some work. It is not fun to program distributed systems, and the distributed systems are everywhere. We desperately need some work here, and I do think that soundness and good type systems are part of the solution. So before I get into the theory of things, my day job looks a lot like this. I have to talk to servers, and the servers they have all of the power but share none of the responsibility. It's like sometimes your messages please the gods and sometimes they do not. That's what it feels like to work with other people's servers. I'll give you a specific example. Google is a notoriously capricious god. They made an official Node.js client to communicate with their servers. I just noticed this. The official Google, the last build is failing. Good for them. So I was helping out a friend with some YouTube API stuff, and so I look in the documentation and I'm like, okay, I think I have what I need. I go to use their official client and not in the TypeScript. I'm like, okay, but the TypeScript and the JavaScript side of things are not actually the same. So I look through the JavaScript, okay, not there either. So there's not a problem there. But it is in the documentation. I reach out to YouTube support, and they're like, okay, yeah, the documentation is sometimes ahead of the client. You can implement this as an HTTP request in this fashion. So I do that, and it's not actually quite right. The output doesn't match the documentation. So go back to YouTube support, gets escalated, and oh no, I'm actually looking for an undocumented API that must be enabled on my account. They did that for me, sent me documentation as a PDF via email, and ta-da, it worked. that is what it feels like to work in the web nowadays. This is not just Google though, and it's kind of everywhere. This like fragmented feeling is really pervasive, and it's also not even just web. It's if you have ever done game development, you will know that these like dynamically loaded libraries on the front end, and you pack the homebrew on your Macintosh. Things get out of sync. Many of you guys are researchers, so Python 2.7 probably keeps you. Gives Python 2.7 PTSD, right? Various programming language and frameworks have tried to do things to reduce this fragmentation. TLA plus, for instance, is not a type system that you would use in TypeScript. It is some external thing to prevent certain classes of errors. All of these kind of fit into that same bucket where they are trying to prevent certain classes of errors amongst the many computers that are trying to interact. When I've been really thinking about this problem, and there's a few underlying things that are all unified here. There's no machine verifiable link between documentations, types, schemas, requests, responses, and addresses. All of that is just kind of like ad hoc floating all over the place. And because of all of this, when I am a client, I'm implementing a client, I am forced to take the server's word for everything. When they return 400 or 500, I actually do not know whether or not they're telling the truth. I just have to take their word for it. The errors that they give me, they're not documented anywhere. So I receive errors, and the errors are not documented. So I have to, often parse strings and work in meat language instead of letting the computers handle classes of errors. And all of this is versioned with something that looks like /API/v2, which is just an ad hoc versioning system built on top of all of this. And there's no real standard, and even the companies themselves don't follow their own patterns. So all of these, I feel like, stem from a common attribution error, common attribution errors. There's no automatic way to blame misbehaving servers. When you're a child, the way that you stop misbehaving is to play blame games, right? You have to figure out the rules of who's correct and who's not. Don't hit your sister. Well, she poked my eyes. He put a leech in my shoe. She called me ugly. He started it, right? You have to like do this whole thing to figure out what the formality is. That's how you develop manners. So when I'm thinking about playing these blame games, here's an example of a network. You are Albert, and your ex-wife Betty, she has the address and the mail, and you want to just send very nice letters to your daughter Clara, and the courts have given some parameters about how often and what kind of letters you're able to send, but Betty doesn't want that communication to happen, so it's a whole complicated thing, and there are ways of formalizing the system so that it does work for everybody. That same system can also be used to enforce the opposite situation, where your other ex-wife, Barbara, who you are in very good terms with, and your piece of crap son, Charlie, who you need some information from. Charlie is exceptionally good at predicting the next day's weather, and you also want the courts to be able to enforce some communication there. So this whole blame game hopefully should create a formal system that works in both scenarios and many other scenarios. It's the general premise. What I came up with is this notion of responsible servers. This is if I have all of these properties, I think I'm going to be able to communicate with many different types of servers, hostile, non-hostile, and it should feel pretty good. Like I am reasonably happy with. I'd be reasonably happy as a web developer or a game designer, whatever, working with distributed systems with these types of servers. Now, I tried very hard to make this work with TypeScript land, some of the more popular stuff, but either I am not, I don't have enough energy or patience or brain cells, so I'm off in my own little corner making my own programming language called ScrapScript. ScrapScript is a pure functional programming language like Haskell, but it's shaped like JSON or XML. It's shaped like a data format, but it's got functions, it's got control flow, so it is a full programming language. And it is typed, and the types themselves are data just like anything else. So it has a bunch of really interesting properties. One other thing that is nice about my programming language, ScrapScript, which has an awful name. It's hard to even say it. It's like choking on like dry crackers or something. Every chunk of the language, I call them scraps, every sub-program, everything in the language can be replaced with a hash of that chunk. And so the language itself ends up being shaped, programs end up being shaped like Merkle trees. So that also provides some interesting properties. Everything becomes content addressable. You can store a whole bunch of stuff wherever, and you can always guarantee that you will get the same program eventually if it's the scraps are stored on different computers. And if we already have all this cryptography junk lying around, it makes sense to sign these little snippets of code. And so authorship can be verified. You can prevent certain types of rot and forgery from occurring in your package managers with this kind of stuff. And it's a cool system. The monkey at the monkey on the typewriter at the Wizard conference. I made a thing in my language that might do some of these things. And the really dumb current thing I have is the use contracts to specify server can say, hey, I am going to be at this place, an IP address, and I'm going to be here for a certain amount of time. I commit to being here. If you're here late, it will be unsafe, and I will abide for this period of time at this period of place by some protocol. So this is type definition, request and response are type variables. So here's what it might look like. Without dependent types, you have to use some DSL to be able to define the shapes of things at the value level. But this is the general notion, right? It should make sense. Obviously, there's already one big thing that all of you are probably thinking. What's up with unsafe at, right? Like that, it's a timestamp, and timestamp is not correct. Like this breaks the laws of physics. You are 100% right, and that's part of why I'm at the Wizard conference. I have no idea how to improve upon this. This seems to work good enough at non-relativistic speeds, but if you have any ideas on how to make this work, without without introducing hard timestamps, that'd be wonderful. Here's, text is small, but I gave an example of what it might look like full conversation or full API. This is like an API definition that you can get from this server, and you can go and have a full request and response party. Okay, but once again, these are monkey solutions to monkey problems. I am at the Wizard conference. Why am I not complaining at the monkey conference? I want, what would be amazing is if we could get something like this working, and we can know that it's correct, right? Like you guys have all of these mathematical tools to ensure that something like this could have some nice guarantees, and I've not been able to find any monkey tools for this, and the Wizard tools that I have found seem insufficient. So I think I'm going to talk about that next. Before that, I'm at the Unsound workshop, and some of you may have already noticed, I'm not talking about unsound systems, I'm talking about incomplete systems. A formal system is unsound if you can construct a contradiction from a blank slate, right? But I'm really not talking about that. I'm talking about propositions that I want to be unsound in some system. It's like car traffic. The road may be well constructed, everybody may be obeying the rules, and so the whole system is sound, but traffic still can occur, right? Like there are unpleasant externalities that could happen at high levels. So I'm really talking about this, which I think is I've heard the word safety being thrown around. That might be a better word for these properties. It's sound but unsafe. I've been calling this property soundless in the system. The wizards would say that the propositions are independent of the formal system. I like soundless. The tree falls in the forest, doesn't make a sound, blah, 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 blah. So thank you for being here today, and thank you for listening to me. I'm going to get into more details. Here are some possible properties. I'm going to go through quite a bunch of different properties that we might want in a responsible server contract protocol, right? Bunch of different properties. This is the collection of things that I think would be fun to formalize at some point that I cannot find any way to formalize right now for the most part. So first thing is you have a protocol. We have this contract, right, between two computers. How can we guarantee that the contract, the thing underneath the contract, can be amended and still have the whole system remain coherent, right? Like that is a very nice property to have that I don't think I have. Let's see, gRPC kind of has it, but you can only add fields to your contract over time. Universal, does this thing have to be, I would prefer if this thing did not have to be implemented in scrap script. I do not want to, that just sounds like a bad thing. It sounds like this should be a shape of something that can be extended to JSON, XML, etc. That would be nice if we'd have responsible servers across the world in any language. The properties of contracts that we might want. Can the contracts themselves, can both server and client, can they agree upon updates and do those updates? Or do they have to wait till the unsafe period elapses? Is there always, actually, I'll wait for that one. Can contracts overlap, right? One way of thinking about doing migrations is that you have a contract that goes until some time, and you start the next contract before that, and you allow the client to kind of hop contracts. They have some window. So that pattern implements a lot of problems for both client and server, and so there's a lot of interesting problems there once you get into the weeds. Contracts themselves, whether or not blame can always be assigned. You can imagine a contract where it is not completely clear, even though there are terms, it is not completely clear who bungled something on the request or the response, right? You can also imagine contracts that aren't completely deterministic, that might not be a quality that you want. A whole bunch of really cool qualities that you can start thinking about with these contracts. And once again, I think some of these, I feel like wizard tools really work well, and some of them I'm having trouble finding clean ways of thinking and expressing this. So I would love to know, amongst all these properties I've talked about, like which ones are, like some of these properties may just be absolutely impossible. Some of them may be mutually exclusive, right? It may be the case that you can't have unambiguous contracts that are also arbitratable by a third party, right? Could be the case, something like that. Cap theorem type stuff, right? I have tried thinking, using a few different systems to model a lot of these properties. Some seem to work okay and some don't. PyCalculus for this type of problems was kind of where I started and wasn't really able to make it work how I wanted. With all these types floating around, just didn't feel good. Linear types didn't feel good either for most of the time. Temporal type theory it uses sheaves to create behaviors, and it's like, I think somewhat it starts getting into like the category theory stuff, and I think that's a little just overkill. But we do have some good stuff. What is the good stuff that might be promising? The first is this one paper I found that talks about contracts for web services. Sounds within the realm of stuff that I'm talking about so far. And I like it, seems useful. Also, don't quite see a way to get this wizard tool clearly into the monkey typewriter realm, but this is a very good start. You can guarantee a lot of really nice properties when you start talking about lots of computers working together. So I do like this. Scrap script with the shape of thing that I talked about with dependent types seems to work pretty well. You can just use dependent types and to check the unsafe thing at compile time and make sure that you can tune that. So there's a clear working implementation. The problem that I don't like is, yes, you can have something that checks at compile time, but there's no real extra niceties to reason about this thing and implement nice static analysis tools on top. So another thing I was thinking is, okay, throw some refinement types in there, right? So at the bottom, I threw like, okay, if you construct something like this internally or or in the syntax, you can say, okay, this contract has like a subtype of location and for a given amount of time, right? It's valid for this. That way, you can have a you can write code that will complain if you're sending it to the wrong place, or if you're sending it at a time that's invalid. It will add expiration dates to certain parts of your code. So that could be something interesting. With this, one nice thing is that you can fetch contracts from a remote source and still act upon them, right? You don't know the explicit time and place, but you can write code that survives that not knowledge at compile time, and still you're able to make coherent programs. So that's a nice feature. Another nice feature is you can compose these contracts. So you can have multiple times and places that things work. In a migration scenario, you might have something like this, where it's like, okay, I have some implementation, and I just want to make sure that my implementation is good throughout this window. And so you can do things like this. If we steal from Rust's lifetimes model, it might be good to have like these addresses and durations. Just give them unique type variables in the program, like lifetimes, but they would be something like server lifetimes. I have thought about this, and it seems pretty unergonomic, but could be fruitful. There are some nice properties about it. Yes, with the session types, right, it might be nice to be able to enforce strict ordering of these contracts. So you have to send a message before you receive. You have to request an OTP code on your phone, like the SMS message, before you submit it. Right? Like you can enforce ordering like that with session types and a few of these other models. But yeah, that's it. Thank you for coming, and I hope this was either entertaining or informative. Yeah, thank you.
Any questions? Please feel free to ask. Okay, I'll start again. All right. Yeah, very interesting topic to present here. We are, so I think in this community, we often say that session types are the supposed solution to this kind of problems, right? Distributed programming and protocols. You said that you looked into them, and they seem to be part of the solution. So in what way are they lacking? Or what's the missing part that you need from them? Is it the part about evolution, like ensuring that the system can be changed while avoiding ad hoc versioning?
So as a programming language designer, let's take Rust as a model, because I think Rust is the most popular implementer of session-like types.
Sure.
Right? If you really start thinking about how you would implement remote session types, it becomes just, I have not been able to think of an ergonomic way to put this in a language where you're like talking about like a server lifetime. Mm-hmm. And I think the reason is because you need to bounce between address literals and sometimes you want an address literal, you want an actual IP address, and sometimes you just kind of want a reference to some IP address and you want that to be consistent, like kind of like how Rust does memory management.
Mm.
But how do I put this? So again, with Rust, I think it works because you're talking about, oh, I don't care exactly which block of memory I have. I just want to make sure that block of memory is reserved. But with this internet stuff, you really do need to specify specific things. You need specific blocks of IP addresses. I don't feel like those models tend to work well together. I hope that's like clear.
Well, okay, but well, at least in the research literature, I think session types are not really concerned with this sort of low-level details. It's more about expressing protocols in types, right? And so I don't really see how that's so what you're describing is a problem. The fact that you need to refer to IP addresses, sure. Sometimes you don't know the specific IP address. You mentioned dependent types, so normally you can use dependent types for this. I'm not sure exactly what you mean by dependent types when you say you're using dependent types, but the principle of dependent types is that you have types that depend on values, and you still can reason about these things even if you don't have the value at compile time, right? But you can still reason about it. Okay? And you can discover information incrementally about it and resolve things in this way. So I guess I'm not really seeing the limitation of session types, but maybe because you're talking about specifically the Rust incarnation of session types, but actually it means something possibly quite more general in research. Maybe you should look into that.
Yeah, I definitely can look into that and will. There might be existing literature that is exactly what I need.
We can discuss this more offline if you're interested. And I also was wondering that session types are. I don't think they're concerned with the evolution of systems, which is one of the problem you described, right? That you want to address. It sounds interesting to look into this, and maybe the answer is to include some form of gradual typing, right? Like maybe the session type cannot be fully known in advance, and at some point you need some graduality, right? Some more runtime checks when you cannot foresee every possible future evolution. I don't know. That's just a thought. Yeah.
Yeah, I think there are like clear implementations that would work if you were to sacrifice some. I listed a bunch of properties, right? And so certain obvious applications of session types, at least for me, like or gradual typing, it's like, okay, I get a lot of these properties, but there's some properties that I cannot obviously keep that I might want, and so I think that's like probably a fruitful next step for me, is figuring out which systems of thought allow me to keep certain properties, which implementations allow me to keep certain properties. Can I implement something unambiguously, etc.
Which trade-offs you have to make?
Because I don't even know what the trade-offs are.
Yeah.
I want to know what the trade-offs are.
Mm-hmm. Okay. Well, it sounds like a worthy endeavor. Anyway.
Worthy endeavor. Any other questions? I'm also be around all week for the most part.
Okay. If there's no other question, let's stop here. We're out of time anyway. Okay. And thanks to the speaker again.
Thank you.
Okay, where is it?
In the system preference, display, left, display, yeah, true tone off. Yeah.
All right. Sorry. Wait. Okay. All right. Hello, everyone. So let's start the afternoon session by talking about distributive subtyping with finitary and infinitary unions and intersections. All right. So please interrupt me if anything is unclear, right? I think we have time, right, for some questions, including during the talk. So intersection and union types. How many of you are familiar with intersections and unions? Maybe, yeah? It's getting pretty popular, right? So you have intersections of the form S and T, or S intersected with T, which represent types that contain the values of both S and T. You also have union types dually, right, for types that contain values that are either in S or T or both. And sometimes in math notation, we use this square cup and square cap notation to denote that this is an algebraic operation. It doesn't necessarily correspond to a set intersection or a set union, but more like an algebraic operation. And in languages, in actual programming languages, we use the ampersand and pipe characters. So here's an example in many languages with intersection types that also have record types, such as this record type, which is a record of field A of type S and field B of type T. Then that record would be a subtype of the intersection of the records made of each individual fields, right? And this means that basically the record type can be thought of having both the type, just a record of A with type S and a record of B with type T, right? This is thanks to record width subtyping, the fact that you can forget some of the fields of a record by upcasting. And as for an example of unions, you could have a union if you have a branching statement, for example, that returns two different values in each branch, one different value in each branch. And if these two values don't have exactly the same type, then you may get a union type as a result. So here you have a value that could be either foo or bar at runtime. Okay, so here's my question. Should intersections and unions distribute over function types? And if so, how? Okay, so let's look at an example and let's vote. So for example, this general intersection of two function types from S to T and from U to V, can we say that it's equal to a function type even when the types don't match, right? If S is not equal to U or T is not equal to V. So who think this cannot be done? There should be no distributivity. Okay. So one thing we can do that's kind of obvious in a way is that you can say that if the parameters are the same, then the result can be then you can distribute the intersection into the result, right? So if you have a function that gives us a T when you give it a S, and it also gives us a U when you give it a S, it kind of makes sense to say that after you give it an S, it gives you both a T and a U, right? Kind of. It depends, right? It might be sound in some systems and not in others. Raise your hand if you think this looks good. Wow, nobody. One person. Okay. So actually, this doesn't really work in the presence of side effects, but that's another story. How about same results? If you have this intersection, you can say that, well, in practice, it means the function, you can give it either an S or a U, right? It doesn't matter. And it will always return to U or T. So raise your hand if you think this should be done. Yeah. Sure, it makes sense, right? This one does make more sense. How about full distributivity? That's if you have arbitrary types in the two function types, you can actually distribute the intersection into a union on the left and an intersection on the right. That's weird. Who thinks that that can be done? Nobody? I think it can be done, okay. There's also ways of saying that, well, actually, you can equate the intersection to the function type where you have intersections on both sides. And in fact, so this one is a subtype of that one, right? But you don't have the subtyping the other way, using the normal function subtyping rule. But it is possible to decree by fiat that these two types are actually the same type, right? They're equivalent. And similarly, you can also do it with a union. It also holds in one direction, but not the other. And you can decide in some systems that actually it holds in both directions as an axiom. So there are many, many options, right? So which one should you pick? And the answer is that there's no right answer, and it depends on the context. It depends on your language. And here's a quick overview of what languages do. So actually, both Scala and Ceylon have full distributivity, the weird rule I showed that distributes into unions and intersections. Okay? TypeScript doesn't actually do any distributivity, but you have things like CDUs, which use set theoretic types. I'm going to explain a bit later, which does distribute when both parameters or both results are the same, but doesn't do full distributivity. Okay? And some historical language, like research language, like Foresight, which does also something similar. So how come, right? Well, first let's look at some examples. So in TypeScript, you don't have any distributivity. So actually, it takes the first option. And actually, in TypeScript, you cannot really say anything because unions are just weird. They're not commutative, right? You cannot swap the components of a union and have the program still type check in all cases. So maybe let's not talk about TypeScript. Let's talk about a more serious language with similar capabilities. And this would be, for example, CDUs, the language with semantic subtyping, where every type is really thought of, or really formalized as a set of value, an actual set of the values that inhabit it. And there's no general distributivity of intersections over arrows, but you can distribute them when the parameters or result are the same as I mentioned. So if you represent this visually, it's like, yeah, you have these two types, and then their intersection corresponds precisely. So the intersection of the corresponding sets of values corresponds precisely to the intersection type in semantic subtyping. Okay, so that's just a graphical, visual way of seeing it. And so in Scala 3 and Ceylon, as I mentioned, you have full distributivity, you have this rule, okay? And how could that be? Because after all, think of an intersection of concrete types, int to int and string to string. Scala and Ceylon tell us this is the same as int or int to int and string. So a function that takes ints to ints and strings to strings, meaning it has this intersection type, also returns a value that is both when given either. Weird, right? And so it turns out that this is actually sound in many cases. And in this particular MS Struct core language that we designed in our research group earlier, we do use the full distributivity, and it's actually crucial in having principal type inference, because if you cannot do that, then you cannot reduce some awkward constraints and without having to do some backtracking, and you cannot achieve principal types. So there is very important. But then we generalize our system by adding more powerful types, including first-class polymorphic types. So decidability goes out of the window, and you don't really have complete principal type inference anymore, but you have very powerful types like for A to A, okay? And with polymorphic subtyping, so for example, you can upcast this for all type into a normal type, right, by instantiating it. The problem is that this is no longer compatible with full distributivity, okay? Because this type, this for all type, you can instantiate it into both sides of this intersection. And so by the definition of intersections, it means that the type is a subtype of the intersection. And clearly this is not the same as this, right? And so we have to avoid it in this case. So basically you can think of the ML's struct approach, the previous one, as having a simpler lattice of types, and intersection corresponds to picking the meat in that lattice, and there's no polymorphic types in the lattice, and so it happens that it's perfectly fine to pick that type as the meat. But here it's no longer the case. But still, it's not really clear what you should actually do in practice and what are the implications. So there are also other approaches like compositional programming, a research language, where intersected function types decay into intersections on both sides. It's fine. And for size, as I mentioned before. A related issue is, how about arbitrary type constructors like class types? What if you have C of int intersected with C of string? Do you have C of int and string? Not in general, right? But what if C is covariant? Is it the case? It's not actually clear, because even in Scala, which is implemented like that, if C is covariant, then you can distribute the intersection inside. This is not really completely clear, right? It's not actually justified by the theory of Scala. You would have to add new axioms to support this. And so this is currently an open issue in Scala, right? There's an issue in the bug tracker. People don't really know, is it really good to do, fine to do that or not? And as we've seen, it's not quite clear when you cannot do that. So first, let me give some background on unions and intersections, just to make sure we're on the same page, a little bit more formal background. So intersection types, they can be summarized in this short slide as the following typing rules. So this is mostly slightly reformulated rules than the rules given by Copo and Desani Ciancaglini in 1980. So what these rules say is just that well, you have the normal rules for functions and applications, and then you have intersection introduction, where if some term T can be typed as T1, and it can also be typed as T2, then you can type T as the intersection. And then you can eliminate the intersection. If you have actual values with the intersection, you can pick one of the two, depending on which you want to use for this particular use site. Okay? Now you can generalize this notion to subtyping. Yeah, let's first talk about subtyping like this. So in 1983, BCD subtyping was proposed, which stands for the initials of the authors. And this is basically a way of making subtyping aware of intersections, so that you can have these kind of coercions at the type level. What if so intersections are idempotent, so you can take a T and make it an intersection of T and T, and you can eliminate, forget about some components of it through subtyping, and you can apply subtyping concurrently inside the intersection, right? And this system did have this bit fishy rule that distributes the intersection inside, which is not sound in the presence of side effects in a system like this. Okay. And so an interesting view of subtyping, I think it's useful for the intuition how to interpret subtyping is as retyping. So the normal subtyping rule that most systems have is that if you have a term T of type S and you know that S is less than T, then the term T also has type T, right? Capital T. But how do you define subtyping, and which subtyping relations should hold? And I think it's useful to think of subtyping as basically a no-op coercion, right? So a coercion that you can do very easily by just reinterpreting the term by just retyping the term. So you can add a rule that conceptually represents what subtyping is. Subtype S is a subtype of T. If assuming some variable X has type S, you can conclude that the same variable has type T. So that's just one way you can conceptualize subtyping as a retyping. And if you do that, then you can actually derive all of these rules, all of these intersection subtyping rules from the original intersection typing rules, along with a rule for introduction of top types, right? So just using normal typing rules, which are kind of simpler, you can derive all of these thanks to retyping. So that's pretty cool. Another thing that I want to emphasize is that the intersection introduction rule is not necessary to support in full. So as a reminder, let me just quickly recap it. Intersection introduction says that any term T, if it can be typed independently at type T1 and T2, can then be typed at the intersection of T1 and T2. But actually, it's a very powerful rule. It makes intersection type system basically undecidable because it makes well-typedness equivalent to strong reduction, to strong normalization, right? So it's too powerful, but it's possible to avoid that very general rule and instead use more specific rules. And as an example, in TypeScript, this doesn't actually hold. Like if you have, let's see, so you can type a function, a lambda from A to A as both number to number and boolean to boolean. Independently, you can do that, that's fine. But you cannot type it as the intersection. So that demonstrates that in TypeScript and similar languages, you actually do not have general intersection introduction. But what you can do in TypeScript is that you can define overloaded functions using function signatures like this, and that's basically, that acts as one very specific kind of intersection introduction, specifically for functions, right? And so what you do is that you provide declarations that are more specific, and then a less specific implementation, where if you want to type check it, you have to use less specific types inside, right? And you may do some pattern matching or some tests inside to determine in which case you are. And then TypeScript will type check that the function can be given both signatures independently. And thanks to this, it will allow you to say that the function has the intersection type of these two things, right? Everything clear so far? So that's for intersection. Now for union types, which were introduced a bit later than intersection types, but still a long time ago. You have also union introduction, union elimination. The elimination rule is a bit more complicated. There's no need to go over it. What's interesting to know is that, again, you can derive subtyping from the typing rules using just retyping. And so the subtyping looks like this for unions. It's completely dual to intersections, so no surprises. In their paper from 1995, where they present subtyping for union types, Barbanera et al. Also proposed a distributivity for function types, right? So if you intersect these two function types, you get the one that I showed before. When the result types are the same, you can distribute the intersection into a union in the parameter. So there's been a recent resurgence of interest in both academia and industry for these types, right? Intersections and unions, which is why most of you already have heard of them. Okay, and moreover, most type systems with intersections and unions distribute one into the other, right? So this is not actually problematic, but just as a side note. And so I mentioned that I wanted to talk not only about finite intersections and unions, which is what we've seen so far, but also infinite or infinitary unions and intersections. Basically, you can think of for all types and existential types as infinite intersections or infinite unions, right? So for A, f of A is the same as f of int and then string and blah, blah, blah. So if you have a polymorphic function that for any A takes an A and return an A, then it's really the same as a function that can take any particular type. Like when given an int, it gives you an int. When given a string, it gives you a string, etc., etc. Right? And the neat thing about this is that you can use the same reasoning principle that you use for normal unions and intersections and lift them to the infinitary setting most of the time, right? Okay, so finally I come to the meat of the talk, which is my argument that you can elucidate the difference between these different distributivity rules as the divide between church and Curry-style semantics. So as a reminder, church-style semantics says that the terms you're manipulating are internally typed. They have a type, the function parameters have a type, and so it's always known what's the type of things, and the semantics is given on these internally typed terms, right? Whereas in Curry-style semantics, the types don't matter for the semantics of the term. All terms have semantics, even those that don't have a well-defined type. And you typically provide types externally. On the existing term, you say, oh, this particular term has this type. And you use types to prevent, you use types to exclude terms that misbehave, right? Terms that do bad things like crash. And so basically, you can think of intersection-based overloading as fundamentally Curry-style, right? Remember the intersection introduction rule. It said that you needed to type the same term as two completely different types at the same time, right? Simultaneously. And this is why this is a Curry-style language feature. It asks you to not have any internal type, but to consider that a term can have many different unrelated types at the same time. Okay, and this fits particularly well for TypeScript, right? Because TypeScript is just JavaScript with types given externally, but actually the semantics is given by JavaScript itself. You can just erase the types immediately, and the types don't participate in the semantics at all. Whereas a language like Scala is Curry-style. So in Scala, the lambda term x to x doesn't mean anything on its own, right? And if you write it as part of a bigger expression, like list of 123.map of x to x, then the compiler automatically elaborates this implicitly to a fully internally typed term, right? Where the parameter type is given. And only terms that have these types have semantics. Otherwise, they just cannot be compiled, you know? And so such a given lambda term cannot have multiple unrelated types simultaneously. It's a church-style language. So how does church-style explain full distributivity? Now we can actually justify this crazy rule I showed earlier that didn't seem to make any sense. But actually it makes sense. So think of it this way. Any function that you have in Scala, call it f, right? That happens to be found to have both types s to t and u to v. So somehow you know that the f has both types. So it also has the intersection type, right? S to t intersected with u to v. Then since it's a single value, and values cannot have multiple unrelated types at the same time, there must exist one single domain and one single codomain that describe this function, right? And both S and U must have been obtained by narrowing this original domain D, right? Through function covariance. So for example, if you had a function that says that goes from object to object, you can narrow that to a function that goes from int to object or string to object, right? And similarly for the codomain, right? There's only one true codomain for the function, but it may have been widened into these other T and B types, right? And so, so we must have the following subtyping relations, which allows us to justify this, the rule that says that this function f, okay, which has type D to C by assumption, also has type union of S and U to intersection of U and V. Do you see where I'm going with this? So I think that's the reason why full distributivity is fine in Scala and not in a language like TypeScript where it's wildly unsound, right? You can also generalize this reasoning to arbitrary class constructors, such as the class for functions. So in Scala, functions are not really primitives. The primitives are classes, and functions are just one particular type of class. So the function of one argument, the type of functions of one argument is represented by the abstract class function one. And in the standard library, function one takes two type parameters, but in terms of foundations, Scala is defined in terms of dependent object types calculus. And in this calculus, you don't have actual type parameters for classes. These are syntax trigger for type members. So it's like you have types inside the class, the abstract class, and they're not defined. They don't have a given value. And moreover, you have a method apply that corresponds to actually calling the function. And so this, on one hand, is how Scala represents functions. And on the other hand, the dependent object types calculus treats objects as basically records of both values and types, right? And if you remember the idea that you can derive subtyping rules through retyping and some form of eta expansion, that was the case for function subtyping. Well, consider that you can also eta expand records, right? So if you have the following record that has type T, you can, where each label, each field is taken from an existing term T, projected to the field of the same name, right? Then you can tell that the term T has type capital T. So that's eta expansion for records. And if you accept this eta expansion for records, and if you also accept retyping, the rule I gave to derive subtyping relations, then you do again get full distributivity of constructors, of class constructors. Okay, so I don't have time to go into the details. You have to trust me on this, but we can talk more about it separately. All right. So let's conclude quickly. I tried to, in this talk, examine the problem of distributive subtyping from first principles, going back to the roots. What are intersections, unions, and how to interpret subtyping in a way that subtyping between these type forms can be justified intuitively. And I tried to explain that the differences in distributivity between different languages actually comes from the church and Curry style divide between the two styles of semantics. Okay, and that's why some rules may be completely unsound in one language, but completely fine in the other, right? Okay, so thanks. That's it. And do you have any questions?
Yeah, thank you. Nice talk. So, as somebody who's delved into the specific things, if you were to design a language, which typing system would you pick?
I think it depends. I think both have pros and cons. Currently, we're designing a language called MLScript, which has Curry-style semantics. And so we also want first-class polymorphism, which is another thing I didn't actually explicitly mention, but if you want first-class polymorphism, you have to use a Curry-style language, basically, right? If you want polymorphic subtyping. And so for this reason, currently we are using Curry-style. But I think it also makes sense to do what Scala does and do more magic at compilation time based on the types. That can also be very useful. Yeah. So, not sure.
I see. Very cool. Thank you.
Thanks. Any other questions? Okay, so if not, let's move to the next talk, because it's time. So next, which one do we have? Is the speaker here?
No, it's online.
Oh, it's an online talk. Okay.
Yeah, I think it will wire.
Yes. So. Yeah. So the next talk is online. We have to wire the. Yeah.
The presenter is still not. Like,
He's not there.
It's not online.
Let's wait a couple of minutes, I guess. Has he responded?
No.
No.
I mean, technically, they should join the test sessions, and we were trying to warn them half an hour ago, but they just did not show up.
Oh well. Let me see. Maybe I can try to message them.
Do you know when if they're can you go to the script? No, just cover script.
This workshop.
Okay, it's only one person. That's it. Yeah. And we better wait for half an hour if they're not showing up, because we also have 2 more remote talks, and we don't want to change the schedule for
Oh,
them,
right.
because
Yeah. We don't want to change the schedule for sure. So let's see.
can you ask when anyone will come back responding or being on the bonus channel? But yeah, they are missing. It's the
I'm gonna send him a reminder. So he just has to join the Discord server. The Unsound.
They did join the server.
Oh, they did join.
They joined the server.
Yeah,
They're
yeah.
not here, like
So,
in the channel.
So they're like server, but not in the channel.
Yeah, like
in
we
the channel.
added them and they should respond to us. But like normally they should be in one of these voice channels, and we just drag them to the channel where they're presenting.
What's his status?
No, this person is the later one. Then it's the remote. Oh, okay, sorry.
So do you have a link? To the, you have a link to the channel? They can send him directly. Okay, I can try to navigate there.
It's called test session.
It's called test
Oh,
sessions. Or
Okay.
they reply.
let's me see. No, his supervisor replied. Is it test sessions?
Yeah.
I sent you a link if you.
Thanks. Yeah, there's no official
Yes.
session. Okay, so we're trying to join the speaker. Sorry about that. May take
you're interested in the paper that this is based on, just between functional programming and OOP.
Angela, please note that there is no photography.
So, my working type theoretic definition of object-oriented programming is that it consists of three parts. One is codata types, or programming against interfaces. A second part is subtyping. And the third part is open recursion, or late binding. But in this talk, I will restrict myself to this aspect of object-oriented programming against interfaces in the type theoretic guise of codata types. And to give you some context, this is very close to some of the articles that were written by William Cook on the nature of data abstraction. So let's start with a concrete example, the Booleans in the functional programming version. So here we have a data type of Booleans, which can either be true or false, and we have the negation function, which is defined by pattern matching. So the Booleans are defined as a data type, and negations or observations on Booleans are defined by pattern matching. Here, on the other hand, we have the same program, but now we represent Booleans as a codata type with one observation, negation, which returns another Boolean. The Booleans true and false are now represented using something called co-pattern matching, which says how these Booleans behave when the negation observation is called on them. Another way to see this is that these Booleans are just implementing the negation interface. More generally, these two representations, the data representation, which is close to the functional programming version, and the codata version, which is close to the object-oriented style of defining types by interfaces or methods that you can call on them, they are related by two program transformations. In the one direction, we can go from any data type to a codata type using refunctionalization. And in the other direction, we can take any codata type and transform it into a data type using defunctionalization. This might look a bit surprising because if you've seen defunctionalization in the past, you probably have seen it applied to the function type. But the function type is just a specific instance of a codata type with one observation. So here we have the two programs again in the data and in the codata style. And how are these two types related? Well, one way to see the relationship between the data type version and the codata type version is that both programs can be represented as a matrix. A matrix which contains the canonical ways to construct Booleans as the columns and the canonical ways to destruct them as the rows of this matrix. The two programs are then just two linearizations of this matrix. And this transformation can be mechanized. So for example, here we have an example from our programming language that the paper is based on, where you can change the transformation, change the representation of a type using just the click of a button. Here I transformed the data type bool into a codata type. One of our big contributions was that we now extended this to dependent types. So here we have the same data type of Booleans that we had before, but we additionally have the Martin-Löf equality type on top. And we have a proof that a negation is involutive. That is, if we apply negation twice, then we obtain the original result. This proof that negation is involutive is here written as an observation of a Boolean called self, where the self type occurs in the return type of the function neg inverse. And the proof proceeds just by pattern matching on all possible booleans. If we refunctionalize this program, then we get this program where we have left the representation of the equality type as before, but booleans are now represented as a codata type with two methods: the negation and the property that every boolean that we define, that the negation method that we implement for any boolean has to be involutive. So we have these method calls where the object on which I call the method occurs in the return type of the method. And every object that I define now comes with a correctness proof. So whenever I have to implement a verified interface, then I also have to provide the proof that the implementation is correct. Just to show you that this also works in our implementation, this is the program I just talked about, where we can change the representation of a type with the click of a button. So what have we actually shown in the paper? We have presented a type theory with no built-in types. So for example, both the non-dependent and the dependent p-type or dependent function type are user-defined codata types. We have given a proof of type soundness for the system, so we do not have a problem with soundness. And we have shown that de- and refunctionalization is total and type preserving. We can also de- and refunctionalize any types that occur in indices of type constructors and which are normalized and compared during type checking. In order to do this, to de- and refunctionalize types which are normalized and compared during type checking, we have to apply some restrictions on the beta and eta quality that we can use during type checking. But I wanted to present it Unsound because in the related work section we have one very big open problem, which has to do with the problem of consistency. So when we started writing the paper, we started with a different title. The first title under which we submitted the paper was the proof expression problem. And the reviewers rightfully rejected that title. Why? Because the system is not consistent, and therefore we cannot say that it applies to proofs, since system is not consistent. But I want to give you an idea of what our original vision for the system is. So consider an ordinary definition of an algebraic data type for expressions, here with three constructors for variables, lambda abstractions, and function application. And consider a proof of type soundness that you would write in an ordinary proof assistant, like based on dependent types like coq or lean. So you would probably implement the substitution lemma, as well as proof of progress and preservation. So we have done this, and in a system we can refunctionalize this data type in order to obtain the following codata type. Here, expressions are defined by all the methods that we've proven by induction or recursion over the original constructors of the data type. For example, you can see that progress and preservation were defined by pattern matching on all the constructors of expressions, and you also see that we had to prove the substitution lemma, also by pattern matching on all possible constructors of the expression data type. And to show that this works in real time, so here's part of the proof of the soundness theorem. where we can just change the representation of the type, and the rest of the proof is automatically transformed. So this was our original vision for the paper, and why we called it the proof expression problem, because it applies to the expression problem in the context of proofs.
We welcome you to Los Angeles.
So we think that we are very close with our system. We have an extremely powerful refactoring tool for proof engineers, where you can change the representation of any data or codata type which occurs in a proof, unless the system is inconsistent. And by inconsistent, I mean that every type is inhabited. We have three sources of inconsistency in our system. We use the type in type axiom. We have no checks for positivity of data and codata type declarations. And we do not implement any termination or productivity checks. So on the one hand, we could just implement what other proof assistants implement. So we could implement a hierarchy of type universes. We could check for positivity of recursive occurrences in data and codata type declarations. And we could implement termination and productivity checks, for example, by checking for a structural recursion, and that every recursive call of a function is done on structurally smaller arguments. But the de- and refunctionalized programs would no longer check. So I will now give you three examples to show why this is the case. So the first problem has to do with universe hierarchies. So I said that we currently use the type in type axiom, which is known to be inconsistent thanks to Girard and to the simplification by Herkins. So we do know that we need to introduce some hierarchy of type on universes. The problem is that that we do not know how to annotate the correct universe levels after defunctionalization. This problem has also been described by Huang and Yalop in a paper from last year called Defunctionalization with Dependent Types. The second problem has to do with the positivity of type declarations, and can be observed in this example. Here we define a set of natural numbers with two methods. The member method, which allows to check whether a given natural number occurs and returns a Boolean, and the set union operation, which applied to a set allows to compute the union with a different set. The problem is that we have a negative occurrence of the type not set here. But this type can be the result of refunctionalizing an ordinary ACTA or COC program using only strictly positive data types. We could, for example, implement sets of natural numbers as binary trees, implement the member and union operation by induction on the tree constructors, and also implement the union operation. This program would then type check in most proof assistants like COC or ACTA, but if I refunctionalize this codata type, then I would obtain this definition, which contains the negative occurrence. This is also related to the binary methods problem from the OOP literature. And the third problem has to do with termination and productivity checking. Here we see a program that can be written in most proof assistants. We first have a data type declaration of the piano natural numbers, and we have to check that data type declaration. Next, we have to check the termination of plus. We can do this because the the recursive call of plus is applied to a structurally smaller argument. And thirdly, we have to check the termination of the multiplication function, where we can assume that plus has already been proved total. So we have a natural order of declarations. We first check the totality of plus, and then we check the totality of multiplication. If we refunctionalize this program, on the other hand, then we obtain the following program. In this program, it is no longer clear how to check for totality, for termination and productivity. So how do we declare the dependency of multiplication on addition if the successor and zero are mutually recursive? We must somehow first construct partial objects, S and Z, for which only plus is defined. And only in the second step can we construct the complete objects, which are defined, for which both the plus and the multiplication method are defined. So, yeah, it's very, very difficult, but you can follow the development of the project on our website. We have a distinguished artifact at UPSLA, the implementation, and yes, you can also try out the examples on the website. So I thank you for your attention. I'm very sorry that, but yeah, thank you very much.
Hello, David? Hello, can you hear us? Yeah, okay.
I mean, you can just,
I'm sorry, yeah. It's super loud here. And
Okay, I have some question.
I mean,
you can say the question.
say the question.
Okay.
We'll also be on.
Okay, so thanks for the talk. The solution you hinted at of constructing partial objects sounds to me like it has to do with initialization checking, which is a problem that people in some communities have grappled with. I'm speaking too fast, maybe. So do you see any parallel between object initialization checking and your solution to the inconsistency? Any parallel between these two problems? I can take it. Yeah.
so one question I see, whether I see any parallels between object initialization and our solution to the consistency problem. Yes, I think the problems are closely related, but it is still ongoing work, and yes. I will be there for the entire week, so I'm very happy to chat with other people. because I think there is a strong connection between kind of verification efforts for object-oriented languages and like the initialization problem and the kind of problem that we are observing when we try to change the representation of a type. So yes, I do think there is a very strong relationship between
On behalf of Los Angeles
what we are
Airports,
kind of the solution we are looking for and the kind of
Please
solution
note
that
there is
people in
no
the
photography
OOP space
allowed in
are
the
looking
federal
for.
inspection area.
Yeah, can you say thank you? We can bring the speaker again. Yeah, there's no other question, right? Yeah. Okay. So, well.
And I got 4x3. I guess we have a couple minutes because we're waiting to be in sync with the rest of the conference.
You're Nick?
No, I'm
Good, good, okay. Good. Do you need it?
No, no. Do you need it?
No. Should I use it? You can use this one. Yeah.
Do you need to introduce the speaker?
Yes, but not now. We are waiting for 4 minutes.
Hey.
I guess we should start again. So the next speaker is Colin Gordon, who will talk about Java method local inner classes and why they are unsound. Okay.
All right. Hi. Thanks for the introduction. So I'm going to talk today about something that we stumbled across in some work I'm doing with Marco and Nick, who are on the slide here but couldn't be here in person today, along with a few other folks. The context for this is basically we are working on an interesting object calculus, which I won't actually talk about today. But the thing that's interesting there is that in that calculus, the creation of new objects and new types is a little unique. Basically, all of the class definitions end up looking like they're located at the allocation sites, which ends up being fairly close to Java's method local inner classes and how those work. And if you're wondering what is a method local inner class, I'll say what it is in a minute. But as we were formalizing this, it turns out there are a couple wrinkles that we weren't expecting. We didn't see these written down anywhere. And so we did, we have solutions, but we kind of did what is natural to do and asked, okay, we're seeing this interesting scenario in this core calculus. Let's see what mainstream languages, heavily used languages that have analogous features do in analogous situations. And it turns out that, at least for Java, it does things that are not quite what we would expect, right? So first of all, let's talk about what even is a method local inner class. So the name is suggestive, but it is a little bit of a niche feature. Not everyone is aware that Java lets you do this. Java lets you declare a class inside a method. Right? So on the right here, we have a method tasks, and we have a method local inner class here, a specialized runnable. It has constructors, it has fields, methods, whatever else we want to throw in there. And usually when we do this with not to keep the instances of this type purely local to the method, but because we usually use this to implement some external interface, inherit from some external class. But by virtue of it being named, we can actually use the name and construct it multiple times. It's a little more convenient than if you tried to make this happen with anonymous inner classes directly. And now if I gave you like the featherweight Java paper and said, okay, go add this to the basic featherweight Java calculus and prove that it's sound, you wouldn't hit any problems, right? So this feature by itself makes a lot of sense, it's convenient. So where do we hit the problem? And the problem crops up when we have these things interacting with generics. So Java allows a combination of a few particular things that play a little poorly together and don't result in any warnings. So I'm going to say what they are to give you a sense, and then we'll talk about a detailed example. So Java lets you have a non-generic method local inner class, like on the previous slide, but it lets you have them in such a way that they somehow capture a dependency on a method-bound generic parameter. So most of us don't write a ton of Java that does this, but Java also lets you bind generic parameters per method invocation. Once these objects escape the local method, they are no longer, it turns out, tied to the particular choice of method generic parameter that they were created under. And because it's non-generic, the Java compiler doesn't give any warnings about casts or instance of checks with that method local inner type. So hopefully I've at least convinced you that there's something a little bit interesting here in this possible interaction, but I'm going to do an example. But ultimately what this lets us do is we can mix up instances of this method local inner class from different method invocations that use different generic parameters, and it leads to some confusion. Right? So here's an example. We could make it more minimal, but I think this is a little more readable. So down at the bottom here, we have this just generic container of x's. You could use list, you could use any other generic type for this example to work through, but we're just going to call it a foo_x. And then up at the top here, we have a class that has a static method that is this problematic generic method, and then we have some main code that's going to trigger some problems. So first thing we do in the static method m is we have an anonymous inner class. It's called myFoo. and it extends foo of x. Right? It happens to capture this x argument to the method, but that particular part's not super critical. The thing to pay attention to is this myFoo is not generic in and of itself, but it's sort of implicitly generic because it does depend on the choice of x here. So choice of, yeah, sorry, actually there are too many x's here. It does depend on the choice of this generic type parameter to the method. Right? So the actual code in this method, there's only 2 lines, and these are kind of the pair of lines together with the way we set up the definition of myFoo that end up being a little bit funny. So the first thing we do on line 4 there is we check, we have this other object, right? And everything in Java is an object unless it's a primitive. And we can ask, is this an instance of myFoo? Right? Now, certainly the first time we call this method, we can't have any myFoos before. So the first time we call this method, this will not be an instance of myFoo, so we allocate one and we return it. If we call this later and we do pass in a myFoo, well, the instance of pass check will pass. It will be a myFoo. And then we cast it to a myFoo, which should work because we just checked that it is a myFoo and we return that. The problem is JVM generics are erased. So what happens here is this instance of can be compiled and it runs, right? And it basically checks, is the class table for this object myFoo? And it can make that check and it can succeed, but because the generics are erased, it doesn't actually check if this is a myFoo from this invocation of the method with this choice of the generic parameter, or if it's a myFoo from a previous invocation with a different generic parameter. And the same thing happens with this cast, right? Same problem again. We cast a myFoo, and the cast succeeds because it has the right class table, but again, the generic parameter is erased, so that part can't be checked. But this code compiles and runs without any compiler warnings. No warnings, no errors. So what goes wrong? So let's talk about this main method. So first thing we do in this main method is we make one call to this method, and we call it with an integer. For that first object, we just pass, it could be anything, so we pass the string anything. We go through, we get to line 4. The string is clearly not a myFoo, so we allocate a new myFoo. It happens to capture this 5 that we passed along the way, and we end up with this sort of object graph on the left here, right? So we have one myFoo that sort of implicitly is supposed to be a myFoo for integers, and it holds 5. Right? Now we do the weird part. We call this method again, but we call it with a different generic parameter. We call it with strings instead of integers. And we also switch which random object we pass in. We pass in now this first myFoo that we got out. So it goes in here on line 4. It now is an instance of myFoo. So that gets negated. So instead of allocating a new one, we get to line 5. We cast it to a myFoo, which it is. And we return that R1 argument as the result, which means that R2 now points to the same object, even though its type says it's supposed to be pointing to a container for strings. It points now to a container for integers. So essentially what we've done is we've implemented a cast from foo of integer to foo of string, but if you tried to do this cast directly in Java, it would complain. It would say, hey, we can't check this cast. Or if you tried instance of with one of these types, it would say, sorry, we can't check this at runtime because of the generics erasure. So it's also worth pointing out here, so what do we mean by unsound? We mean unsound in the sense that there are features of Java that we'll get to that lead to this not corrupting any memory. But this violation, right, this fact that we haven't actually gone out of our way to use some of those particular features of Java I'll talk about later, but we have something that says it should be a container for strings, but is pointing to a container for integers. Right? So this is what we mean by unsoundness. And if we continue execution, line 10 works. Right? So line 10 is using this object as it was meant to be used, as a container for integers. It tries to get the integer out. We print 5. Everything's fine. And then on line 11, when we try to get the string out of this thing that actually contains integers, we get there a class cast exception. So what's going on here? Right, so again, this is a combination of a few things. So my foo is tied to a generic parameter. It cannot have its generic parameter checked when we're doing cast or instance of. And casts to and from, likewise, instance of checks with this, do not yield errors or warnings. But curiously, if you go and just tack on a bracket X on the definition of my foo, suddenly you get errors. So somehow it seems like if this is explicitly generic, the compiler kind of does what we would want. It gives you a warning. But since there's not literally a generic argument list on the declaration of my foo, it's treated as non-generic despite sort of relying on this method generic parameter. So I mentioned earlier that that example was just sort of had this foo type just sort of as a placeholder for a generic kind of container. But you don't actually need that. So you can trigger this all sorts of ways. I won't walk through this one in detail, but you can see the first line of this method M here. We still have a class myFoo. It still depends on this method-bound generic parameter type X, but we're just relying on it being an object. So we don't even need the generic container type. It just escapes as just a regular old object. It can come back in as a regular old object as far as the static type system is concerned. And we have the same instance of and casting trick in there. So a natural question, though, here is, you know, on the previous slide and here, we end up in this case where we have a variable that points to the wrong instantiation of myFoo's sort of implicit generic parameters. What actually throws the exception when we run these example programs? So, courtesy of Compiler Explorer, there's some JVM bytecode down here. It looks like it's a little less readable on this format than when I prepared the slides, but we'll go with it. So this is the JVM bytecode for the two print lines, the last two lines of that first example, where we first print the value in the integer container and then print the value in the so-called string container that actually has an integer. And you'll notice that the second one's a little bit longer, and it's not just because the return is down there at the bottom. So the first call is going to call the object overload of print line, right? So there's a bunch of different overloads for print streams output methods. There's one that just takes object and just calls object.toString and prints that. And when we do this with an integer, that's what gets called, right? Now, the second time, we call a different overload. We call a string-specific overload. And in that case, because this is the output of a generic parameter, the compiler inserts an additional check cast instruction there. The reason for this is because Java also has this feature that now when I talk to students seems a little bit lost to the sands of time, which is raw types, right? So Java has this feature where even though it has generics for backwards compatibility, you can take a generic type like list of t and just treat it as a list and put whatever you want in it. And the compiler will, in certain circumstances like this one, say, we're fetching something out of this generic type, but maybe somebody used it, this object at a raw type somewhere else in the program, we'll stick in a check cast, and that sort of saves things from going too wrong here. But the interaction of these features is totally non-obvious, especially since we don't really teach anybody raw types anymore. They're not really discussed in modern introductions to Java. And I regularly talk to people who are a little younger than me who don't even know they exist. So this is weird, right? And so this is what we are calling an unsoundness, right? Because this is not the expected behavior. And in general, this failure point of this check cast that gets inserted later could, like other raw type situations, be arbitrarily far away from where we mixed up these generic parameters, right? Now, a natural question to follow up with is, okay, so that's Java. Java is not the only language that runs on the JVM. And the other languages that run on the JVM want to interoperate with Java, which has this feature. It has method local inner classes. So the other robust, mature implementations of languages on the JVM also support some form of method local inner class as well. So what do they do? Do they do this any better? Well, Scala is an interesting case. Scala 3.0 does exactly what Java does. Works exactly the same way. No warning, no error, same code gen. Scala 3.4.1, somewhere in there, they added an error. It's not the clearest error. It says that you can't check the cast that we use, and it just says you can't check the cast because it's a local class. But of course, it's not just because it's a local class, it's because it's a local class that also depends on method generics. Right? If there were no generics happening in this example, the cast to my foo would have been totally fine. So, okay, great, that's Scala. How about some other languages? How about Kotlin? Right? So Kotlin's another somewhat younger but growing language on the JVM. So here's a direct transliteration of the first example into Kotlin, and you might notice there's a little squiggly there. There's a little red squiggle. And it turns out that's because Kotlin does actually give you warnings about this. It does say error cannot check for instance of arrays type myFooX. And this is interesting because we didn't declare myFoo as explicitly generic. We did exactly what we do in Java. But Kotlin caught on, hey, there's a dependency here on this method parameter. And so Kotlin actually seems to track this internally, as do newer versions of Scala, and notice, hey, this has a dependency. We need to at least give a warning. Now, you will notice that there is no squiggle on line 10, which is the actual cast. So it gives us a complaint on the instance of equivalent, but it doesn't complain about the cast. If you really wanted to, you could still trick Kotlin by doing the cast, caching the exception, and using that without the instance of check, and then you could get it to work without warnings. So it's not perfect. Kotlin's also interesting because it actually has two kinds of casts. It has so-called safe casts, which are not safe because you can't misuse them. They're safe, quote unquote, because they don't throw exceptions. So they have an as question mark cast operator, which if the cast would fail, instead of throwing an exception, you just get null instead. And in that case, you no longer get an error, but you do get a warning that, hey, this cannot be checked. But again, there's still kind of this hole here with just the regular old possibly failing cast. If you're willing to catch exceptions, you could still trick things, right? So ideally, Kotlin has enough information here. It could issue an error for the cast as well. So what do we do with this? The core issue here really is that there's a method local type that depends on a generic parameter that gets erased, right? So instance of with these method local inner types cannot be checked. Casts with this method local inner class, because it depends implicitly on a generic type parameter, cannot be checked. So we think that the instance of and or the cast should yield an error, or at least a warning, although we think it should be an error, because you just can't perform these checks, right? And we can see that Scala and Kotlin do track enough information that they could give warnings for all of the right cases, right? Kotlin gives the right warning for 2 out of 3 possible sources of unsoundness. Java does none, Scala does 1, right? So if we just change things so that Kotlin actually performs 1 extra check during compilation on that unsafe cast, then Kotlin would be sound, and there's no fundamental reason that other languages can't do the same and be just as thorough. So that apparently went a little faster than expected, but that's all I had planned to say. Okay.
Question.
Thank you. Thanks for the talk. The erasure semantics of Java was an implementation hack done for political reasons so that Sun didn't have to change the virtual machine. So the real, and what you've discovered here is places where in the implementation, the compiler, they should have done these tests and didn't.
Yeah.
The question I have, is there a language design issue, or is it just don't do implementation hacks that don't model the actual language? Does that make sense?
My personal feelings about erased semantics aside, which I suspect agree with yours, if you have made that choice, you can make it sound if you have the checks in the right places. It just seems to be one of those cases where syntactically this method local inner class doesn't have a generic parameter list attached to it, so it gets treated like it's not a generic type, even though there's this extra way of capturing a dependency on it.
For example, they could have done the implementation where there was something like an instance variable which held the value of the generic, that type, so that type could actually be used. And
oh yeah,
it would be useful to know that that design with inner classes really is sound. I gather there's a, what is it, the Waddler stuff, the featherweight Java with inner classes, and I don't know whether it deals with these issues. I suspect it doesn't get quite that much.
Yeah, we haven't seen any formalization of something that mixes both inner classes and generics, which is how we ended up sort of poking in this direction. Because doing the proof for the calculus we're working on, we ran into some kind of funky issues, and our settings are different enough that our solution's a little different than what we're recommending here. Dot? For, that's a good point. I would have to go sit down and look at the details again.
So, which one? Do you mean dot?
He means dependent object types. Which?
DOT, right? Dependent object types? Yeah.
Yes.
So Guillaume Martre, who is on the Scala team, he wrote his thesis on featherweight Scala, which is a bit closer to the actual Scala. And I don't think he formalized local classes, but I think the main reason is that they're easily desugared into top-level classes where this problem doesn't occur. Because then
if you did the desugaring, you would basically add this parameter explicitly, right? Which might actually, we haven't looked at the code, but so we suspect this is what's happening in the Scala compiler and the Kotlin compiler.
So that might be where the error is coming from in the Scala compiler, right? And it's probably the easier way to check for this, to first desugar and then do the check, right?
Yeah, that would be totally equivalent to tracking it as a property of the anonymous method local inner class too. Totally.
Right. Okay. So can you say again? I think I missed it. You said that Scala gives the correct warning in one case, but not in some other cases.
Whoops.
Yeah.
So Scala does flag the warning. It flags the cast, not the instance of, and in some sense you could argue the cast is the more important one. But
it doesn't flag the instance of.
It doesn't flag the instance of.
It's actually a problem.
Yeah, but I mean, that would be probably not what you're expecting and sort of be surprise semantics, but that alone you can't get this kind of unsoundness out of. You need the cast to work too.
Right.
So it does at least flag the cast, but the wording is a little like they wrote half the error message because it depends on not just it being a local class, it's also got to be because it's generic. Because a cast involving a local class that really has no direct or indirect dependencies on a generic parameter, the cast is fine. You can do that and it works just well.
Doesn't that mean that the Scala inner classes are nested inside classes, not nested inside objects, or in this case activation records? Because you've got the issue that you could have two classes. I mean, the question is if you have two instances of one of these things from different method invocations, should they or shouldn't they have the same type? And that's a choice. And another choice is if you have two of these things which I was going to say almost everything has to be nested, I think, inside a method invocation, even if that method invocation is in its pseudo method resulting from a constructor. But you kind of think of it as being nested inside an object or an instance of an enclosing class for the non-static, because all these are non-static inner classes.
Mm-hmm.
Again, should two classes nested inside different instances be the same type?
So
clearly, if you talk like this, Gillard should manifest, and he just has.
So, as you might imagine, as one of the people responsible for this mess, I have a lot to say about it. So there is more than one. Usually, these train wrecks are a result of more than one mistake, and the first mistake is the one that James just mentioned. And the beta people had done this in beta years before and knew that nested classes are properties of instances and not of classes. And some of us at Sun knew this, but the people who actually did the first cut of inner classes did not. And once it was there, it's unfixable. And what Kim called political reasons, otherwise known as compatibility for your actual customers who are not academics. And so there was no way to actually. Yes, yeah, and so these things, are cannot be fixed. But once I saw the title of your talk, I understood what the problem was, and that's a fine thing. My other meta comment is, as you say, no one seems to have analyzed this particular problem because one version of featherweight Java looks at this and one doesn't. And this is the problem with all the formalizations that have occurred, is because unless you have a formalization that does the entire system as it is actually done, which means it does class loaders and reflection and inner classes and serialization and all these things at once in one system, thank you very much, good luck doing that, then all your proofs mean precisely nothing. And that's the problem, right? You can show that something is sound in some fictional world, but it doesn't tell you anything about whether it's sound in reality.
Yeah, I mean, and what you say is exactly true, and it's true of all the other cases of this language feature in this language is unsound. It's, like you said, it's always the same thing because the real languages are so enormous that
is the problem.
It's a Herculean, unmanageable effort to try to formalize all of those details, for sure.
All right, any other questions? Just a quick remark. You mentioned at some point that if Scala kept track of generic parameters, it would be fine. And if there was no generics involved, it wouldn't be a problem. But that's actually not true. Because in Scala, you can use type members and you can have path-dependent types.
Okay, that's
and
fair.
so you could get exactly the same problem without any generic parameter.
So I would argue that if it depends on a type member, then it would be a kind of dependency on a generic parameter, right? It would depend on some. It would depend on some type that could come from a different instantiation.
Well, actually, yeah, sure. Right. Yeah. Okay. Thanks again.
Thank you.
So good.
This is Bruno. Hello? Hello?
Oh, yes.
Hi, Bruno, can you hear us?
I can hear you.
Great.
Yeah.
Please give us a sec. Can you share your screen?
Oh, I thought
For
it was
the
already
presentation.
shared. So let me.
You are in the wrong. You are not got wrong. Wait, they moved themselves away.
Yeah, they moved it up. I do need to retract them. And what is this?
No,
Hi, Bruno. Can you share your screen for the slides?
Okay, I just shared. Let me see what happens again. I should share in the pre-talk channel, right?
You don't need to. Just share in this channel.
Just share this channel.
Yep.
Okay. Let's see. Because now I don't see. Oh, I see. I see the screen share. Okay. Okay, and next selection. Okay, can you see it now?
Give us 1 sec. Great. We see it.
Okay. All right.
1 moment. All right. We are ready, and you're good to go.
So the next speaker is Bruno Oliveira from Hong Kong University. He will talk about the inexact superclass problem. Yeah. Please go ahead.
Okay. Okay. Thank you very much. Thank you very much for inviting me to the Unsound workshop. So this talk is about the inexact superclass problem, and let me start by giving a little bit of context about what the problem is about. Basically, this is a problem that arises when we try to type check dynamic inheritance. Okay, so this talk is going to be about inheritance as we see it in object-oriented languages, and in particular, one flavor of inheritance that we see typically in dynamically typed languages, which is this dynamic inheritance flavor. So dynamic inheritance is a common feature in several dynamically typed languages, including JavaScript. So the examples that I'm going to present today are JavaScript and TypeScript programs, essentially. Dynamic inheritance is not a common feature in statically typed languages like Java or C#. Those languages basically have mostly avoided dynamic inheritance, and they use a different variant of inheritance. And mostly they avoid it because of some typing difficulties. However, TypeScript, which attempts to type check JavaScript and has a very rich type system that tries to type check as many JavaScript programs as possible, it supports some mechanism that type checks dynamic inheritance. And what I'm going to show today is that this mechanism is essentially type unsound, and I'm going to analyze the problem a little bit. Why is it type unsound? What are the difficulties? And also point out that the problem is a general one. So if you ever plan to have a language that has a type system that tries to type check dynamic inheritance, you probably have to face this challenge. So basically, the inexact superclass problem gives you a canonical example that illustrates the challenge. And it also illustrates the unsoundness issue that you have in TypeScript. Okay, so let's dig into some background explaining what is this about static and dynamic inheritance. What are the differences? As you know, inheritance is a key feature in many object-oriented languages. It's used for reusability and to extending existing classes. And in this talk, we are going to consider two flavors of inheritance. One is static inheritance, which probably most of you are familiar with. And in static inheritance, the inheritance hierarchy is determined statically at compile time. Okay. And then we have dynamic inheritance. And in dynamic inheritance, you have a more flexible form of inheritance where the actual inheritance hierarchy can be determined at runtime. So let's be concrete, let's look at some programs. Let's look, for example, at this typical Java program here. So here we have a class A with a method greet. Okay, so we defined class A with a method greet. And then we have a class B, which extends this A, so it's a subclass. And here we can see the inheritance. We can see this keyword extends, and we say that B inherits from A, for example. So it's going to inherit all the method implementations from A. Of course, in this case, we are overriding greet. So basically we inherit, but we immediately override. So there's no other methods that we inherit, but it also shows another feature that you normally have in object-oriented languages, which is not just the ability to inherit, but also the ability to override some existing implementations, right? So this method here is overriding the greet method and replacing the implementation with some different implementation. Okay. An important point here, which is related to why we call this static inheritance, is basically that when we have this class declaration, the syntax that we can use here, so class B extends A, in this syntax, the A here is restricted to be essentially the name of a class. Okay, so in particular, so you don't have the flexibility to write other things here. You cannot write another expression or a type that is not a class, etc. So all that you can write here is essentially the name of a class. Okay, so you might have a little bit of flexibility if you have generics. So you might have class with arguments, but essentially you have to write the name of the class plus the type arguments. Okay, so because you write this name of the class, that means that what you're extending is statically known. So you're extending exactly this class A here. Okay, nothing else. So that's what we mean by static inheritance. So now let's try to contrast this with dynamic inheritance. Actually, before that, let me just summarize some things about static inheritance. So this is just a summary. So essentially what happens here is that in static inheritance, we have a statically known superclass. Okay, as I just said, when we have this syntax, class B extends A, A can only be a class name. So this implies that A is always statically known. And the other thing that is important to mention, or one other thing that is important to mention, is that class declarations have a dual role. Okay, so if we come here, so a class declaration declares both a type. For example, there's a type called A whose interface contains a greet method that returns a void. There's a type called B whose interface returns a greet method, return void as well. Okay, so class declarations serve this purpose of declaring a type, and they also serve the purpose of providing an implementation for that type, right? So here, in addition to declaring a type that has a certain interface, you also provide some implementations, okay? So there's a dual role in these class declarations. And one thing to notice here about this dual role is that there's a tight coupling between this type that we are creating and this implementation. They are inseparable in some way, right? So here, when we say class A contains these methods, we are both defining the type that has this interface together with these concrete implementations. Okay, so now we can move to dynamic inheritance and see how it's different. Basically, dynamic inheritance is supported by many languages, including JavaScript. And here we have an example of dynamic inheritance in JavaScript. So we can have a JavaScript function, and this function is called mixin. And mixin is parameterized by base. Base is just a function argument. And then what this mixin does is that it returns a class. So it creates a class. Okay, so it creates a class, and the class that it returns is a class that extends base. Base is the superclass here. And what is base? Well, base is just this argument to the function. Okay. So what this means is that this class is going to be created at runtime. So we are going to create this class at runtime, and the super class of this class is going to be provided as the argument of this function, right? So you're only going to be able to exactly determine what the super class of this new class is at runtime after you run this function application here, right? So here, this class extends base, and it's a class that is going to have this greet method. And here, differently from what we have in static inheritance, we have that base is just a regular program variable, right? So it's not the name of a class, as in static inheritance. It's just the name of a variable. And in fact, in JavaScript, you can, here at this position, you can write an arbitrary expression. So you could have an expression, for example, another expression that, let's say, a function call that then returns a class. Okay, and that class is going to be the superclass of this new class. So essentially, here we say that this is dynamic inheritance because the inheritance is going to be determined at runtime. So it's not statically determined, but it will be determined at runtime. Okay. So to summarize, to give you a summary of the characteristics of dynamic inheritance, one characteristic is that the superclass is determined at runtime. And in particular, you can parameterize over the superclass. So you can pass a base class as an argument, and then create a new class with that base class there in terms of inheriting from that base class. So another interesting point is that when you have this flexibility, then you get this notion of a first class class. Okay, so in most in languages like Java, C# and so on, traditional languages, classes are second class. Okay, so you cannot pass a class as an argument. You cannot create, you cannot return a class from a method or a function. Okay, but when you have dynamic inheritance, typically you also have first class classes. You can pass classes as arguments. You can return classes, as we can see here, as results. Okay, so they are first class values in exactly the same sense as first class functions in functional programming. Okay, and this gives you greater flexibility. So it enables various very dynamic forms of inheritance. You can have dynamic mixins, dynamic traits. You can even have virtual classes and family polymorphism. Okay, and another interesting point is that unlike static inheritance, where you have this very tight coupling between the class type and the implementation, so here you decouple the class type from the concrete implementation, and we will see that this here is important for the inexact superclass problem. Okay, So now I told you about JavaScript. So this is dynamic inheritance in JavaScript. So let me tell you now about TypeScript. So tries to type check this dynamic inheritance. Okay. And here we can see an example, and I'm going to explain a few more things about this in the next slides. But we can basically annotate the JavaScript code that we wrote previously with a few additional types. In particular, now the function mixin gets parameterized by a type, so this t-base. And this type t-base extends constructor. Okay, and constructor means that basically t-base is essentially a class. Okay, so basically this constraint is saying so that the t-base is the type of a class basically. And now we say that base, our argument to this function, as the type of base is t-base. Okay, so here we essentially know the interface of the superclass. The interface of the superclass is this t-base, and base is the implementation, if you wish, of the superclass. So here, in TypeScript, now we can write, we still write the same code. So we still write that class extends base, and that this base has this t-base interface. So how does this work? So let me just tell you a few more things about this. So as I said, this constructor, so here is not very important to understand the details, but it basically says that constructor is something that can be instantiated with new. So you can use new with some arguments, and it's going to return you an object essentially. But to abstract things a little bit, you can just think of this type as representing a class that can be instantiated with any number of arguments and returns an object. So this kind of pattern and idea is documented in the TypeScript documentation. So where they use they use the name mixins, so they call this code structure that we have been using before mixins, and what they are documenting in this web page here is how you can type check the mixins in TypeScript, and basically this constructor that is documented there. Okay, right. So this is how TypeScript type checks the first class classes. Okay, and now before I go into the inexact superclass problem, I want to talk about one more thing, which is overriding. Okay, so I want to go through overriding in JavaScript, and I want to go through overriding in TypeScript. So in JavaScript, okay, JavaScript is a dynamically typed language. So overriding is completely unconstrained. Okay, so there are no constraints on overriding. And essentially, methods in subclasses can override methods in superclasses with different types. So we can see an example here. So we can have a class A that has a method M that returns 48. So here 48 is a number. Okay. And then we have a subclass, class B, that extends the A. And now we are going to override M. And we are just going to return a string. Okay, so here we return a string. Obviously, there's no problem doing this in JavaScript. JavaScript doesn't have a type system, so this is fine. So it's allowed, and now you would have a class B where the M returns a string. So this is clearly not type safe, right? Because you here you're actually changing the interface. At least if you have some expectations. But anyway, that's not a goal of JavaScript. So nothing to worry about at this point. How about TypeScript? So TypeScript needs to be a bit more careful because it has a type system, and it tries to ensure type safety. And the way that TypeScript works is not that different from the way that Java, C#, C++ works. So it has some restrictions on the overridden methods to ensure that these overridden methods have compatible types. So the example in the previous slide does not type check in TypeScript. TypeScript is going to complain that the type of M is not compatible. And here we can see an example that does type check. So obviously, if you have a class A with a method M that returns 48, a number, you can override, you can create a class B that extends A and then overrides M to return another number. So in this case, this works, of course, because the types are compatible. Okay. So now we can finally move to this inexact superclass problem. So what is this problem about? And so this problem, as we shall see, arises because the exact type of the superclass is unknown at compile time. Okay, so basically you have the flexibility to pass an implementation of the superclass, and you have the and you can specify the expected type of that superclass, but these two types don't necessarily have to match the actual type of the superclass with the expected type of the superclass. They don't have to match, okay? And in particular, the actual type of the superclass may be a subtype of the expected type of the superclass. And this is a key difference compared to static inheritance here, okay? And it can lead to type-safe overriding, and that's what I'm going to show you, okay? So, so then let's look at the inexact superclass problem with a concrete example. So here, what we have is a class A. This is going to be our superclass, okay? So class A is going to be our superclass, and this class A defines two methods. One method M that returns a string, and one method N that calls M. So here, this is quite important. So you call M, and here, of course, you're expecting a string. So you're calling some methods that rely on M returning a string. So the important point here is to note that N depends on M via self-reference, okay? And it's expecting that the M returns a string. So now we are going to try to create a subclass using dynamic inheritance. So we are going to write a function mixin that is similar to the function mixin that we wrote previously. Okay, so where we are parameterizing the mixin by the superclass, and we are saying that we have a certain expected type for the superclass. Okay, and here this t-base doesn't say much. Okay, so it just says that there's a superclass, and basically superclass here doesn't expect anything in the superclass, doesn't expect any methods. TypeScript does allow you to specify a concrete interface, okay, but this doesn't matter. So you could say that t-base contains an A and a B and so on. This is allowed, but actually we will see that this doesn't matter for the inexact problem. Okay, but here basically the t-base, just think of it as the interface of the superclass. Okay, and here now we define a class, and we define it to have a method M. But of course, by the semantics of JavaScript, so what happens here is that if it so happens that this base actually contains an M, this M will be overridden. So so here, when we are writing this code will have the ability to override any M that is in base. So if there's an M in base, it's going to be overridden. Okay, and that's another important point to remember. So here, then after defining this mixin, we are going to instantiate mixin and A. So we are going to basically create a class B, and this class B is going to be the resulting class of running this mixin parameterized with the A. Okay. So the important thing to remember is that A has an M of a different type, has an M of type string in base. So that M is going to be overridden. Okay, so you create a new class that extends the A. You're going to override the M in that class. You still contain the N. Okay, so now what's going to happen? So now what's going to happen is if you try to instantiate B, okay, so this B is going to be a class that contains this implementation M and this implementation N here. Okay. And this is going to give you a runtime error because now N is going to call M and expect that the M gives you a string, but the M that you actually contain gives you an integer. Okay, and this is basically the issue that happens here, the inexact superclass problem. Okay, I think I should, in the interest of time, I should go ahead. So this part I already explained here. So let me just go to this slide here. So it's useful to take a step back and just see what features are needed to trigger this problem. So basically, we need self-references. Okay, so the self-references are needed because the superclass relies on methods that depends on other methods. And we need inheritance, dynamic inheritance. Okay, and it's useful to mention that multiple inheritance would make this problem worse, but we don't have to worry about that in this talk. Okay, so but basically, once we have self-references and this dynamic single inheritance, we are likely to have this inexact superclass problem. Okay, so I think I can skip this. This is the final slides. Okay. Maybe possible solutions. One solution is stick to static inheritance. Okay, so static inheritance doesn't have this problem because you don't have the flexibility to decouple the expected type of the class from the exact type of the superclass. You could try to impose some restrictions. You could remove self-references. That would be probably too restrictive. There are some other, perhaps less restrictive things that you could do. And the other thing you could do, and this is, for example, one of the lines of work that I work on, is you can try to make the dynamic semantics enforce information hiding and having some other types of constraints, disjointness constraints. And there are solutions along these lines, so I've been working on them. The CP language, which is one programming language we develop in my group, for example, provides a solution for this inexact problem. Okay, and okay, I think I will stop here. But basically, the inexact superclass problem highlights this type safety issue that can arise with dynamic inheritance. So if you want to create a language that supports dynamic inheritance, you probably need to pay attention to this issue. Okay, and I'm ready for questions.
Okay, thank you. We have a question.
I don't know if these are questions or comments. First of all, this is nice to draw attention to this problem, and I didn't know you actually had a system that actually solves it. This is Gilad Brock. I've thought about this in the context of type checking Newspeak, which of course would have this problem if you tried to type check it. I guess when you say enforce that only the statically known information is known, that implies that when someone tries to pass in a class, you're going to be able to check that it somehow violates that by having extra methods that might, because it's not only that they could conflict, you could have extra methods that are added later in an overriding subclass somewhere that you didn't know about, and they could conflict with whatever methods you happen to have in the incoming class. So you, I assume you're taking care of all that. And a meta comment, I assume you know, this goes back to the record calculi of Mitchell and Cardelli from like '89 or so when they did record update and they found out that doesn't work. Last comment, I'm not sure, but your JavaScript example might just end up working because JavaScript might turn the integer into a string.
I think this one doesn't work because it's a method call. I remember trying this. I did have an example before where it just worked because JavaScript does lots of implicit conversions. I would double check, but I believe in this case we checked that because we had some previous examples like with integers and strings where JavaScript would just convert the string to an integer. Okay, and that works because it does this implicit conversion at runtime. But I believe that this one, I'll double check, but I believe that this one gives you that it doesn't contain the method.
Okay, cool.
Okay. Yes.
Yeah, you were about to say something?
I was just going to comment a little bit about maybe CP. Yeah, so basically CP, what it does is that it has an unusual semantics. So it's a bit unusual, and there's basically subtyping there is coercive. So when you have an upcast, actually it creates kind of a proxy around the original object, if you want, that will hide all the extra information that you shouldn't rely on. Okay, and that's basically what this sentence here means. So that's quite unusual compared to other programming languages.
Okay, so we have another question.
Hi, yeah, this is Madhu Sridharan. This is pretty cool work. One other point in the design space I'd be curious about your thought on. It doesn't give you static safety, but the fact that you, in this code example, it's kind of called a mix-in, which to me implies that maybe the intent was that M is not supposed to be overriding something from the base class. And if you look at, say, Racket's object system, you have to explicitly, when you're declaring a method in a class, declare whether you intend to be overriding something from your superclass or not. And if you didn't do that in this example, you would still get a runtime error, but you would get it at the point when you invoke mixin rather than later on when you invoke n. So it doesn't give you static safety, but there's just another point in the design space where you might get a more, I think, sensible error. Because again, I'm guessing the intent in writing this mixin function wasn't that m would be overriding a method.
Mm-hmm. Right. So that wasn't the intent. I think this could happen accidentally. That's the point, right? So it could be that by accident your subclass implements more methods, and by accident they clash with the your superclass implements more methods, and by accident they clash with what you have in the subclass. So I do know that Racket also supports first class classes, so they have a different approach and different solution. I don't remember now the details, but yeah, thank you for pointing out.
Sure. Yeah. In Racket, I think you would get an error right at this method call that you've highlighted.
Okay. All right.
All right. Any other question from the audience? I also had a question that it seems you didn't list all the possibilities to fix this problem, which you could also be more specific in the type system, right? More specific about the class that you want to mix in. And in fact, I think you could express this requirements on the base class using our system supergroup. You would just need to specify as an annotation in the base class type the requirements that this base class is allowed to make on the this value. Does this make sense to you?
I think that is related to, let me see. I had a sentence about that. Right. So I think it's related to this point. So basically, you're saying. So you're saying specifying the requirements on the superclass, right?
Yeah. So in our system, if you want to define a mixing component that uses this binding, it needs to be explicit about what it needs from this, and so that becomes part of its type right? And you cannot. So you would have to you have to parameterize the base class with the requirement it needs on the this binding, basically.
So that is also supported in TypeScript. So TypeScript also supports this. It's so they have they basically have a generic version of this constructor here. I didn't show the code with that because it's a bit more complicated. But they have a generic version of this constructor here, which has a generic argument that then you can use to specify the interface that you want for the superclass.
I didn't know they had that. Okay. Mm-hmm.
They have that.
Cool.
So it's in this web page. Here. Okay, so if you go there, I think it's called gconstruct.
Okay.
In that web page, and but it doesn't help. It doesn't help. Because the point here is that, okay, you can say that the interface of the superclass contains two methods, right? So, and so on. But here this point is related. You have to anticipate. So in the superclass, of course, you're going to create a superclass that is is a subtype of the expected type. So you can create whatever methods you want, as long as one. So it might contain those two methods that you expect, but it can contain other things, right? And if one of these other things that it contains is a method of that is overridden here, then you get the same problem. So specifying.
Well, but if that method is being used in a way that would be problematic, it would appear in the interface that's expected of the this instance. In order to call anything on this, you would need to specify that as part of the this annotation. In our system, at least, if you want to use this, you need to say what you expect the type of this to be.
Yes. Okay. So maybe you have a mechanism for that in Super OOP. So you're saying that when you use the this in Super OOP, so you're saying here, right? So here you would specify that this can only call.
Yeah, you would say the type that this must have, and then this should be matched with whatever the subclass wants to create as the final this value.
But in here, for example, if I specify this class, I would say that this can call M.
Yeah,
right?
And the type you expect from that.
Right. But so you could say that, okay. And for simplicity, let's assume here T-base just says, I only expect that the superclass is empty.
Yeah, if
right?
you do that, then you cannot upcast A to this, right? because you cannot get rid of these requirements are contravariant, right? You cannot get rid of them.
Okay. All right. So I haven't checked that part of super OOP, but if you have
so
a
to be
way
clear,
to do
super
it,
OOP doesn't have first class classes at this point, but
yeah.
but it's like a natural extension, right?
Right. Maybe it's a solution.
I
as
think
well.
it's another design point in the many solutions you propose.
Okay.
Yeah. Okay, cool. Thanks for the answers. I think we're out of time, right? So let's stop here and let's thank Bruno again.
Thank you.
Okay, thanks for joining remotely, and I'll talk to you later.
Yeah. All right. See you. Bye.